Hello everyone, this is the second video of Engineering Electromagnetics, a problem solving course. In this video, we are going to solve all problems of the chapter 2, Coulomb's law and electric field intensity. Here is our reference, Engineering Electromagnetics. In the previous video, we solved all problems of the chapter 1, vector analysis, and now here in this video, we are going to solve all n chapter problems of the chapter 2. Similar to the previous chapter, first, you should read the chapter carefully, solve the examples inside the chapter, and then come back to this video to solve the end chapter problems one by one. However, during solving the problems, we will have a quick review on the sections of these chapters, course content, and review equations. Anyway, so let's start by the first problem of the chapter 2, problem 2.1. 3-point charges of equal magnitude Q are located at x equal to negative 2, y equal to positive 2, and y equal to negative square root of 2. Yes, here we have these 3-point charges. Locations are given. I used these indices Q1, Q2, and Q3. But we know that amplitude, the magnitude of these charges are the same, equal to Q. Find the coordinates of a fourth positive charge, also of magnitude Q, that will yield a zero net electric field at the origin. Not too complex, yes? So in this problem, first we should calculate the electric field generated by these 3-point charges at the origin, and then place another point charge on xy plane in such a way that we get zero net electric field at the origin. Okay, so what is the electric field generated by a point charge at the origin in this problem? Let's review the equation of the electric field first. As you know, the electric field is defined based on the electric force, based on Coulomb's law. Yes, you remember this important equation, the electric force between 2-point charges Q1 and Q2 is modeled using this equation based on Coulomb's law. And this force, right, between these 2-point charges can be attractive or repulsive, unlike the force of gravity, right? Gravitational force that is always attractive between two mass. So here we have Q1 and Q2. This is distance between these 2-point charges, or depending on the sign of Q1 and Q2, we can have attractive force between these 2-point charges or repulsive. Okay? The amplitude of the electric force is equal to K, that is a proportionality constant, times Q1, Q2 divided by R2. If we use just the amplitudes, we calculate the amplitude of the force. But considering vector definitions, we can write the equation of the force using unit vectors. For example, here in this figure, As you can see, this is the F2 force applied on point Q2. This is origin. R1 is the location of the point 1, Q1. R2 is the location of the point 2. And here, R12 is a vector from the point 1 to the point 2. As you know, R12 is R2 minus R1. This is a unit vector from the point 1 to the point 2. Finally, F2 is equal to this one. Now F is a vector, okay? Is equal to Q1, Q2 divided by 4 pi epsilon 0, R12 to the power 2. This is the distance times this unit vector. You know that this unit vector is equal to R12 divided by the amplitude, okay? This one. So you can replace this into this equation. So we can calculate the force applied on the point 1 using this equation. As you can see here, the force F1 and F2, their amplitudes are the same, but their directions are in opposite of each other. Okay, if you consider these vectors. So this is definition of the force. Okay, using these equations, we have these definitions using vector notations. And electric field intensity is defined based on the force. As you know, we use a test charge and place the test charge in different locations of the space that we are going to calculate the electric field intensity. And if we divide the force applied on the test charge divided by its charge value, we can calculate the electric field intensity. So these equations are explained here in this reference. And finally, we have this equation, the electric field of a point charge, this equation. So here, if you consider this point charge Q1, if you consider a spherical coordinate system and place this at the origin of the spherical coordinate system, the electric field for an arbitrary point R is equal to this one. Yes, Q1 divided by 4 pi epsilon 0 R to the power 2. This is the distance from the point, distance from the origin, times AR, a unit vector in the direction of the radial axis in the spherical coordinate system. So this is the equation. Here we have a more generalized format for this equation when the point charge is located at this arbitrary location, R prime. So here we have this equation. If we place the point charge here in this arbitrary location, considering this important figure, here is the origin. R prime is the location of the point charge Q. Okay, is denoted by X prime, Y prime, Z prime. And R is the location of the point that we are going to calculate the electric field intensity on it. Yes, for this point. So this is the vector R minus R prime, this vector. And here is the equation of the electric field intensity for one point charge. Here is E, that is a function of r. This arbitrary point, a general point r, is q divided by 4 pi epsilon 0. 1 divided by 4 pi epsilon 0, I use this k notation for it, proportionality constant. We use this notation when we solve the problems of this chapter. So, yes, times the distance between r and r prime to the power 2 times the unit vector. The unit vector is r minus r prime divided by its amplitude. Finally, we can write this important equation. Okay? And considering the x, y, z components, we have this important equation. So here I can calculate the field, the electric field intensity generated by the point 1, 2, and 3 origin, this point, and then calculate the total electric field due to these 3 points to find the location of the point number 4. So here in this equation, for the first point, Q1, R1 prime is equal to negative 2 times AX. Okay, this is the location of the point 1. So let me copy this figure here. Where is the location of the point 1? Is you should consider this vector. Okay, 2 is distance of the point from the origin. Okay, so this green vector is r prime 1, that is equal to negative 2 times ax, unit vector in the direction of the x axis. And this is the electric field at the origin generated by the Q1. Yes. So here I used this notation. E at the origin due to Q1 is equal to Q divided by 4 pi epsilon 0 times distance to the power 2. Distance of Q1 from the origin is 2. Is 2 to the power 2 times a unit vector in the direction of the electric field, or in the direction of the force if you consider a test charge here. The unit vector in this direction is ax. Okay, so here we have this equation. What about the second point, q2? Q2 is here. The r prime, let me use this color. This is r2 prime, that is equal to 2 times a sub y, and this is the electric field generated by Q2. Yes, is in this direction. So electric field at the origin due to Q2 is equal to negative Q divided by 4 pi epsilon 0 times distance of the point from the origin to the power 2, 2 to the power 2 times a unit vector in the direction of the electric field. That is negative AY. I consider the negative sign here. What about the third point, Q3? This is R3 prime. This is the location, right, of the third point. R prime 3 is negative square root of 2 times a sub y. And this is the electric field, the direction of the electric field generated by the point charge number 3 is in the direction of the a y. Okay, the positive direction of the y axis. So here, this is r prime, the electric field at the origin due to q3 is q divided by 4 pi epsilon 0 times distance to the power 2, that is square root of 2 times the unit vector in the direction of the electric field. that is A sub y, is in this direction. So, what is the electric field, the total electric field generated by Q1, Q2, and Q3? We can use superposition principle. Okay, these point charged are in free space, and we use the superposition principle and sum up these equations. So finally, we will have this equation. Okay, I calculated electric fields using the MATLAB and I generated this figure. This is the electric field at the origin generated by Q1, this blue vector. This is the electric field generated by Q2. This one, this orange one, is the electric field generated by the Q3. And this purple one is summation of the electric fields generated by Q1, Q2, and Q3. So the electric field generated by the point charge number 4 should be in negative direction of this purple one. So in that case, the summation of all of these vectors will be 0. Okay? So the electric field generated by the point charge number 4 at the origin must be equal to negative of E total generated by Q1, Q2, and Q3. In this case, the net value of the electric field at the origin is 0. So E at the origin due to Q4 is equal to this one. And we should rewrite this equation in this format to find R prime. We are looking for the location of the point charge number 4. So here we can rewrite this equation into this format, and then in this format, this is a unit vector now. Okay, the amplitude of this vector is a square root of 2. If we divide it by the square root of 2, this will be a unit vector. This is the distance of the point from the origin, or the amplitude of the R4 prime. Okay, finally, we can find the location of the point charge number 4. This is the x coordinate times the amplitude, right? We can find the x and y position of the point number 4. That is here, right? Approximately. So you can check the solution at the end of the reference for the chapter 2, problem 2.1. Yes, a simple problem, but important equations, notations. These two notations are very important and we will use in this video, right, again and again. These two important points, R and R prime. This is the this R prime is the source point. Okay, this is the source point, and R is the test point, the point that we are going to calculate the electric field, right, at it. So the test point and the source point are R prime. Here I wrote this M file for the problem 1 to visualize the electric field intensities generated by point charges. So here I consider this arbitrary value for the point charge Q in this problem equal to 1 nanocoulomb. This is the epsilon 0. What is the value of the epsilon 0? You remember that? the value is equal to 8.85 times 10 to the power negative 12. Okay, this number. So here, this is the proportionality constant, 1 divided by 4 pi epsilon 0 k. What is the value of the electric field intensity due to the point charge 1 at the origin? Is this one. Okay, this is AX, and this is the value of the force, the amplitude. E0 due to Q2 is equal to this one. The direction is in the negative direction of the y-axis, is 0 and negative 1, or negative a sub y. E at the origin due to Q3 is this one, the amplitude, and the direction is 0 and 1. This is a sub y. Okay, so this is the summation, and the electric field generated by the point charge number 4 is negative of this summation. Okay, so here just I visualized these vectors, and if you run this M file, you can generate this beautiful image. Okay, the electric field intensity generated by Q1, Q2, Q3, the summation, and the electric field due to the point charge must be in opposite direction of the summation of these electric fields. So finally, we have zero net electric field intensity at the origin. Anyway, so let's go for the next problem. Problem 2.2. Point charges of 1 nanocoulomb and negative 2 nanocoulomb are located at these two locations, origin and 1, 1, 1, respectively, in free space. Determine the vector force acting on each charge. So as you can see here, the sign of these two charges are opposite. Okay, we have a positive charge here, Q1, and a negative charge, Q2. So we have attractive force. This is F1 and this is F2. The direction of F1 is in the direction of R12, and the direction of the F2 is in opposite direction of R12. So here R12 is the XYZ of the point 2 minus the XYZ of the point 1, that is equal to AX plus AY plus AZ. R21 is negative R12, is this one. We know that the amplitude of F1 and F2 are equal, yes, and is equal to 1 divided by 4 pi epsilon 0 times the amplitude of the product of charges divided by the distance to the power 2. R, that is equal to R12 or R21. The amplitude is important here. So the amplitude of the force, if you replace the numbers in this equation, is equal to 6 nanonewton. Yes, the amplitude of F1 and F2. F1 is the amplitude of F1 times a unit vector in the direction of R12. This is the unit vector. The amplitude of this vector is square root of 3. Yes, if we divide this expression by square root of 3, we will have a unit vector here. So this is F1, and F2 is 6 nanonewton times a unit vector in the direction of R21. Again, we have this R21, we should divide it by its amplitude to have a unit vector. Okay, so first in this problem, we calculated the amplitude of the force and then we used the unit vectors to find the force vectors. Anyway, let's go for the next problem. Problem 2.3. Point charges of 50 nanocoulombs each are located at these points A, B, C, and D, these 4 points in free space. Find the total force acting on the charge at A. So here we have these 4 point charges. We are going to calculate the total force on the charge at the point A. Okay, so first we can calculate the total electric field intensity at the point A, and then we can use the electric field intensity equation to calculate the force applied on the point A. So what is the value of the electric field at the point A due to the point charge B? QB is equal to Q divided by 4 pi epsilon 0, the distance to the power 2. What is the distance of the point B from the point A? Is 1 plus 1 is 2. 2 to the power 2 is 4. The direction of the force is in the x direction, or the direction of the electric field intensity. So let me copy this image. Here we have this electric field at the point A due to the point B. This is EB in this direction. The distance is 2. So the direction of the electric field due to the point charge B is in AX direction. What about the point charge C? The electric field intensity at the point A due to the point charge C is equal to Q divided by 4 pi epsilon 0, distance to the power 2. What is this distance? This is equal to a square root of 2. Yes, 1, 1. This is a square root of 2. Distance to the power 2 is 2 times a unit vector in the direction of the electric field intensity. So here is the direction of the E at the point A due to the point charge C. This unit vector is equal to this one. AX minus AY, we should normalize it. So we should divide this expression by its amplitude, its norm. The norm, the amplitude of this vector is a square root of 2. Here we have this unit vector. What about the field generated by this point charge QD? This is ED. Again, we have this distance. This distance is a square root of 2. And we have this equation, Q divided by 4 pi epsilon 0 times distance to the power 2. A square root of 2 to the power 2 is 2 times a unit vector in the direction of the electric field intensity. This unit vector, that is equal to AX plus AY. We should normalize it. That is equal to this divided by a square root of 2. So the total field intensity, the total electric field intensity at the point A due to point charges B, C, and D is the summation of these three equations. We can use superposition principle. So we will have this electric field and the force applied on point charge A is equal to QE at the point A, the total electric field. As you know, F is equal to QE. Yes, for a point charge, the net electric field intensity in the point charge location times its charge. That is equal to this one. If you replace the numbers 50 nanocoulombs in this equation, we will have this force. As you know, the force is in the direction of AX because Y components of ED and EC cancel each other. So the force will be in the direction of the X axis. The value is equal to 21.5 micronewton. Okay, not Newton meter, micronewton. You should use correct units. Okay, micronewton. Here in MATLAB, I wrote this M file for the problem 3 to calculate the force and check this number. Here we have the charge Q 50 nanocoulombs. Okay, this is the epsilon 0. This is the proportionality constant. This is the electric field at the point A generated by the point charge B. This one, I implemented this equation. This is the unit vector in the direction of the field due to the point charge B. This is the electric field intensity at the point A due to the point charge C. This equation is equal to KQ divided by distance to the power 2 times the unit vector. So this is the unit vector, this one. And this is the electric field due to the point charge D. Yes? So the net electric field intensity is summation of these three vectors, and the force applied on the point charge A is Q times this summation. So if I run this code, as you can see, the value of the F in the x direction is 21.5 micronewton, and in the y direction is 0. I multiplied the force by 1e6 because I want to display it in micronewton unit. Okay, so this is important. Anyway, let's go for the next problem. Problem 2.4. 8 identical point charges of Q each are located at the corners of a cube of side length A, with one charge at the origin and with the three nearest charged at A00, 0A0, and 00A. This cube, we had a similar problem in the chapter 1. Find an expression for the total vector force on the charge at this point. This is actually the point number 7 in our case, assuming free space. So, yes, we have 8-point charge, and we are going to calculate the force applied on the point charge number 7. So we should calculate the electric field intensity at the point 7 due all of these points 1, 2, 3, 4, 5, 6, and 8, and then use the superposition principle to sum up. Finally, use this equation F equal to QE to calculate the force applied on the point charge number 7. We have this important equation. We can use this format or this format in this problem. This is better. The test point R is equal to this one, and for each source point R prime, we should use the correct coordinates. For this problem also, I wrote this M file. Here you can see the length of one cube. I considered it equal to 1. Here we should use this parametric variable A. In MATLAB, I considered it equal to 1 to be able to plot it, and I considered the value of the point charge equal to 1 nanocoulomb. This is the epsilon 0 k location of the point charge. I plot the cube, then I assign indices, and then I calculate the net electric field intensity. So let me run this code. Here we have this cube. Okay, this is the point number 1, 2, 3, 4, 5, 6, 7, and 8. So what is the value of the electric field intensity at the point 7 due to the point 1? As you know, the electric field intensity due to the point 1 at the point 7 is in this direction. Yes, this one. So the value of R1 prime is 0, 0, 0. The location of the point charge 1, the source point, is 0, 0, 0. Okay? So the electric field intensity at the point P, or the point number 7 due to the point Q1, is K Q R minus R prime. R is this one. This is R prime divided by R minus R prime amplitude to the power 3. The amplitude of this vector to the power 3. This value. What about the point charge number 2? If you look at this figure, this is the point number 2. And this blue one, this vector, denotes the direction of the electric field at the point 7 due to the point 2. Okay? So what is the R2 prime? Is A 0 and 0. R2 prime. So R minus R2 prime is this one, and R minus R2 prime amplitude to the power 3 is this one, amplitude of this vector to the power 3. This is R2 prime and this is R. Actually, R is equal to x ax plus y a sub y plus z a sub z. And R prime is x prime ax prime plus y prime ay prime plus z prime times az prime. But you know that in rectangular coordinate system, this is x, y, and z. In the rectangular coordinate system, ax prime is equal to ax. When we transform, when we shift a vector, yes, so the value of vectors, the components will be the same in rectangular coordinate system, but this is not correct for cylindrical or a spherical one. A or, for example, theta in a spherical coordinate system is not equal to a theta when we shift it. Okay, as you know, the value of the vector in a cylindrical coordinate system or a spherical one is depending on coordinates of the point that the vector is attached on it. We solved an important problem in the chapter 1 and highlighted this point. That is very important. So in this case, rectangle 1, these two are equal, these are equal, these are equal, and simply we can do these calculations. Okay, so r2 prime is a00, r is a, r minus r2 prime is 0 a. Similarly, we can repeat the calculations for the rest of the points. Point number 3, the direction of the field, the electric field intensity due to the point 3 is this one in this direction. Due to the point 4 is in this direction, this orange one. Number 5 is this one, this purple one. Number 6 is this green one. And number 8 is this blue one. Okay, perfect. You can visualize the image of this problem in MATLAB using this M file. So here you can find the source points, the locational source points for these point charts and do the same calculations. Finally, if you sum up all of these equations, we will have this total electric field intensity at the point P, the point number 7. Consider that you shouldn't include the point number 7 itself, okay? So this is the net electric field and the force is Q times this electric field intensity at the point number 7. This parametric equation. In MATLAB, I calculated the net electric field at the point number 7 using this for loop. First, I consider this zero value for the electric field intensity at the point number 7. And here I have this loop, these iterations on the point number 1, 2, 3, 4, 5, 6, and 8. This is r minus r prime. Okay, r minus r prime. So this is r prime. R prime is the location of the source point. E is equal to kq r minus r prime divided by the norm, the amplitude of r minus r prime to the power 3. I implemented this equation. So how we can develop a code to calculate the net electric field at the point number 7. When we calculate this electric field for this specific source point, we can add up it with the E7T, the total one, a cumulative summation. Okay, so we plot the electric field and finally we can find the E7T, the norm, the amplitude of the electric field intensity at the point number 7. So this is the calculation after completion of this for loop. Also, I implemented this equation that we calculated here. I want to compare the numbers. Okay, so if I run the code, as you can see, these two are the same. The value, the amplitude of the electric field intensity that we calculated using this for loop, and the amplitude that we calculated using this equation. Okay, using this equation in this important problem. And here I visualized vectors and also labels, okay, for this problem. Anyway, so you can run the M file and redo calculations of this problem. Let's go for the Next problem, problem 2.5. A point charge of 3 nanocoulombs is located at the point 1, 1, and 1 in free space. What charge must be located at this point 1, 3, 2 to cause the y component of the E to be 0 at the origin? Similar to the problem 1. Yes? So again, we have this equation. We have 2 point charges. This is the test point, the location that we are going to calculate the electric field intensities at it, the origin. R1 prime is this one, the Q1. The Q1 charge is 3 nanocoulombs and R2 prime is 132. The value of the Q2 is unknown. So the electric field intensity at origin due to Q1 is Q1 divided by 4 pi epsilon 0 R minus R1 prime divided by R minus R1 prime, the amplitude to the power 3. So here, if you replace the R and R1 prime, we will have this expression. The amplitude of this vector is square root of 3. So to the power 3 is 3 times square root of 3, and this is the R minus R prime. Okay, so this is the value, the y component of the electric field intensity at origin due to Q1. We need the y component. Okay, that is equal to negative Q1 divided by this denominator. What about the Q2? The electric field intensity at origin due to Q2 is this one. R minus R2 prime is this, and R minus R2 prime, the amplitude to the power 2, is 14 times square root of 14. So what is the value of the y component? Is this one. So we are going to set the net value of the y component of the electric field intensity at the origin equal to 0. The electric field intensity at the origin, the y component, due to both Q1 and Q2, is this summation. Okay, this one. So this must be 0. And finally, we can calculate Q2 using this equation. If you replace Q1 in this equation, 3 nanocoulombs, the value of the Q2 will be equal to negative 10.1 nanocoulombs. So let's check the solution from here. Problem 2.5. Negative 10.1 nanocoulombs. Okay, not too complex, easy problem. Let's go for the next problem. Problem 2.6. 2-point charges of equal magnitude Q are positioned at Z equal to plus and minus D divided by 2. This figure, we have these 2-point charges separated from each other by this distance D. If we consider this coordinate system, I consider this cylindrical one. Okay, the value, the distance is from negative d divided by 2 to positive d divided by 2 on z axis. So find the electric field everywhere on z axis, part A, and the part B, find the electric field everywhere on the xy plane. So let's check here what is the equation, again, we have a similar equation for the electric field for point charge. R1 prime is equal to D divided by 2 AZ prime, that is equal to AZ, you know that. That is equal to delta times A sub Z. Yes, here I consider D equal to 2 times delta. And the R2 prime is the location of this point charge is negative D divided by 2 AZ prime, that is equal to AZ. This is equal to negative delta times AZ. And K is equal to 1 divided by 4 pi times epsilon 0. Okay? So we are going to find the electric field everywhere on Z axis. The test point is Z times AZ, an arbitrary point on Z axis. So R minus R1 prime is ZAZ minus delta times AZ. This is equal to Z minus delta times AZ. So the electric field due to the point charge Q, this one, is equal to K Q Z minus delta, Z minus delta, the absolute value to the power 3. Okay, this equation here, this is the actually value of this vector, the Z component, but we need the amplitude of this vector. The amplitude of this vector is the absolute value of this coefficient. And what about the R minus R2 prime is Z, AZ minus delta AZ. So this is plus. Okay, we have this equation, and E, the electric field intensity on Z axis due to this point charge is KQZ plus delta divided by the absolute value of this number to the power 3. So Z can be a positive or a negative number along the Z axis, but delta is positive, is distance divided by 2. Finally, the electric field intensity is summation of E1 and E2, that is equal to KQ times this expression. Okay, this is the value of the electric field intensity due to these 2 point charges on the Z axis. Now let's go for the next part, part B. Find the electric field everywhere on the XY plane. So here, this is the solution of the part B. Again, R1 prime, R2 prime are the same. We didn't change the location of the source points. Just we are going to find the value of the electric field intensity on the XY plane. So if I use the cylindrical coordinate system, R, the test point, is equal to rho times A sub rho. Okay, so if you consider this coordinate system, this is X, this is Y, and this is Z axis. We have 1 point charge here, another one here. This is delta, and this is delta. So let's pick up this arbitrary point on xy plane, this one. Distance of this point from the origin, this is rho, and this is the unit vector a sub rho. So the value of the r, I'm going to use the cylindrical coordinate system, is rho times a sub rho. And this is the r prime 1, r prime 1. This is the r prime 2. So here r minus r prime 1 is this one, and r minus r prime 2 is this one. What is the amplitude of this vector? You know that if you consider this triangle, the amplitude, the distance of the source point from the test point is a square root of delta 2 plus rho to the power 2. So the E1, the electric field intensity due to the point charge 1 is kq rho a sub rho minus delta a sub z divided by rho to the power 2 plus delta to the power 2, the summation to the power 3 divided by 2, or 1.5. Okay, so similarly we can write equations. This is E2, and if we sum up these two equations, we can find the value of the electric field intensity on xy plane. This equation, as you can see, only we have the rho component. Okay, we don't have the z component because the z component of the electric field intensity generated by these 2 point charges cancel each other. Yes, if you consider this figure, this is the, for example, for this point, this is the electric field intensity generated by this point, and this is the electric field intensity generated by this point. Z components are equal in opposite directions, cancel each other, and this is the only component that we have, that is in the direction of the rho. A sub rho, this is the amplitude of the electric field intensity. So how we can check if we calculated this equation correct or not? So let me write this equation is the proportionality constant charge times 2 rho to the power 2 plus delta to the power 2 to the power 3 divided by 2. This is the amplitude. If we consider this condition, rho much higher than delta, for example, this point, when the distance of the test point is much higher than the distance between these 2 point charges, in that case, rho to the power 2 is much higher than delta to the power 2. So we can neglect this term, and we will have this amplitude k times q times 2 rho divided by rho to the power 3. Yes. So this is equal to k times 2 times q divided by rho to the power 2. This is similar to 1 point charge when the value of the charge is equal 2 times q. Yes, so this is correct. When we have this condition, when the distance of the test point is much higher than the distance between these 2 point charges, the electric field is similar to 1 point charge, but we have this charge 2 times q. Okay, these two charges. So in the next problems that we derive electric field intensities, you can do similar approximations to check if you calculated electric field intensities correct or not. These approximations are very useful in future when we do calculations for polarization or for magnetization and so on. Anyway, let's go for the next problem. Problem 2.7. 2 point charges of equal magnitude but of opposite sign are positioned with charge positive q at z equal to d divided by 2, this charge, and charge negative q at z equal to negative d divided by 2. The charges in this configuration form an electric dipole. A. Find the electric field intensity everywhere on the z-axis. B. Evaluate your part A result at the origin. C. Find the electric field intensity everywhere on the xy plane expressing your result as a function of radius rho in cylindrical coordinates. D. Evaluate your part C result at the origin, and finally simplify your part C result for the case in which rho is much higher than D, the distance between these two charges with opposite signs, that is an electric dipole. So this problem is similar to the previous one, but here we have two charges with opposite signs. Okay, so in this case, r1 prime, this charge, this source point is d divided by 2 times az, that is equal to delta times az. I considered d equal to 2 times delta, and r2 prime is negative d divided by 2 times az, or negative delta az. This is the proportionality constant, k. So in the part A, we are going to find the value of the electric field on z-axis. The test point is z times az. We should calculate these two expressions. R minus R1 prime is this one, and this is R minus R2 prime. So we have these two expressions. This is the electric field due to the positive charge. Okay, here we have this equation, and this is the electric field intensity on z-axis due to this negative charge, this one. So if we sum up these two expressions, as you can see here, we have only the az component, right? We will have this equation. E, that is equal E1 plus E2, is equal to this one. And for the part B, we should calculate the value of the electric field intensity at the origin. We should place the value of the Z, right? We should set Z equal to 0. This is equal to negative 2 times K times Q divided by delta to the power 2. Yes, this is obvious from this graph. Okay, so here let me copy this. How much is the value of the electric field at the origin due to this positive charge? Is in this direction, right? This is delta, so the electric field is equal to K Q divided by distance, delta to the power 2. And what is the E2? Is equal to the field generated by this negative charge is also in this direction. This is amplitude, and if we consider the vector, this is the unit vector, negative of az, is in this direction. We have the same for this charge, and finally, this is equal to this one. The net electric field at the origin is negative 2 times K times the charge divided by delta to the power 2. Not too complex, yes? So we have this expression. The next part. To calculate the electric field intensity everywhere on xy plane, again we have this test point. I used the cylindrical coordinate system here, okay, expressing your result as a function of radius in cylindrical coordinates. The test point is rho times a sub rho, r minus r prime 1 is rho times a sub rho minus delta az. This is r1 prime, okay, and this is r minus r2 prime. So this is the value of the electric field intensity on xy plane due to the positive charge. This is E2. If we sum up these two equations, we don't have the A rho component. Okay? They cancel each other and only we have the Z component. So the electric field intensity on xy plane is this one. Okay? So here in this case, you can realize that. Okay? For this dipole structure, let me copy this. If I plot flux lines from this positive charge to this negative charge, we have these flux lines, electric flux lines. Okay, so these are perpendicular on xy plane. So the electric field intensity on xy plane is in the direction of the z-axis, in the negative direction of the az. This equation, so what is the value at the origin? We should place z equal to 0, that is equivalent to rho equal to 0. Okay, this is the same as this one that we calculated. Okay, because the origin is intersection of the xy plane with the z axis. And what if we consider this constraint? In the case that the rho is much higher than d, in this equation, we can neglect this term. So we have rho to the power 3. So the Z component or electric field intensity on xy plane for rho that is much higher than d is equal to this one. This is an interesting result, an important result. Yes, the amplitude of the electric field intensity for an electric dipole reduces by this term. Okay, r to the power 3. So if we have one point charge q, this point charge q, consider this distance r. As you know, the electric field is equal to k times q divided by r2, the amplitude. But for an electric dipole, if you consider this positive q here and this negative q here, on xy plane only we have the z component of the electric field intensity is equal to this expression. Considering this condition, we have this negative k q times d divided by r to the power 3. Yes, so here the unit of the r is meter, the unit of the distance is meter, and here we have r to the power 3. So units are okay, yes, but the rate of reduction is faster for electric dipole. Okay, so this is an important result. Also, we have other structures, quadrupoles, we will discuss in the next problems, and we can calculate the rate of the reduction. So here, for one point charge, E is proportional to 1 divided by R2. For this electric field intensity, the amplitude is proportional to 1 divided by R to the power 3. Interesting. Interesting. Okay. So, yes, this is an important point of this problem. Here in MATLAB, I wrote this M file to visualize the variation of the Ez on XY plane. Okay, so I consider this point charge, this value for Q, 50 nanocoulombs, and I considered this range for X and Y. I calculated the Ez here. Let me implement the correct equation. This is K times Q times, we should consider a distance also. Let me write 1 here. D divided by rho to the power 2. Yes. Plus delta to the power 2. I am going to plot this function. Okay. So here K -1. Actually, let me plot this example first. If we have, yes, this is more clear. Suppose we have this two-dimensional function f that is a function of x and y. This is equal to x to the power 2 plus y to the power 2. You know that we have this surface x, y, and z. We have a surface like this. Okay, this function, this surface, you maybe generated this surface in MATLAB for other courses, for example calculus. How we can plot this surface in MATLAB? Simply I can generate a mesh grid first. X to the power x and y equal to mesh grid. We can change them from -2 0.1 to 2, z or f equal to x to the power 2 pointwise operation, y to the power 2, and use the surf function to visualize this graph. Okay, this example. In our case, I am going to plot the amplitude of electric field intensity on xy plane. Yes, for this electric dipole. This equation, rho is x to the power 2 plus y to the power 2. Okay, so here these are default numbers that I considered. This is equal to, let me write, zero point 0.5 times d, that is delta to the power 2. Yes, delta to the power 2 plus rho to the power 1.5, or 3 divided by 2. So this is Ez. We are going to calculate the amplitude. So let's calculate the absolute value. I changed the x and y from -3 to 3. So let's run the code. As you can see, we have this variation. Okay, so let's use proper labels for this figure, we have x label is x-axis, the y label is the y-axis, and the z label is ez, is the amplitude of the ez. So here, as you can see, we have maximum ez at the center, and this is the rate of the reduction. Okay, the rate of the reduction is proportional to 1 divided by r to the power 3. Interesting for this electric dipole. If you want to set the view from the top z axis, the positive z axis, you can write this command: view, I want to look at this surface from 0, 0 and 1. Yes, so you can see the field intensity on xy plane. This is xy plane when we look at it from the positive z axis. Here we have maximum field, and here we have these reductions. And it's better if you use the equal axis to look at this graph. Okay, a good visualization. Anyway, this is the point of this problem. Let's go for the next problem. Problem 2.8. A crude device for measuring charge consists of two small insulating spheres of radius a, one of which is fixed in position, the other is movable along the x-axis and is subject to a restraining force kx, where k is a spring constant. The uncharged spheres are centered at 0 and x equal to d. The latter is fixed, this one. We have two spheres, this one that is fixed on this location. This is the x-axis. Yes, the distance of the fixed sphere from the origin is d, and x is the amount of movement of this sphere that is attached to this spring with this spring constant k. And after the movement, we have this distance between centers of these two spheres, d minus x. A is the radius of the spheres. If the spheres are given equal and opposite charges of q, obtain the expression by which q may be found as a function of x. Determine the maximum charge that can be measured in terms of epsilon 0, k, and d, and state the separation of the spheres. What happens if a larger charge is applied? So, this is an instrument for measuring electric charge. Okay, so here this is the electric force between these two charges is q to the power 2 4 pi epsilon 0 times d minus x to the power 2 distance. We can consider them as 2-point charges. However, we have a radius a, right? We have two spheres with the radius a, but I used this equation equivalently. I consider a 2-point charge, and this is the electric force applied on this movable charge, and this is the spring force kx. This is the amount of the displacement of this red sphere. At equilibrium, F is equal to Kx. Okay? So the electric force is equal to Kx, and we can calculate Q as a function of D, epsilon 0, and K and X. We know K, we can measure X. Yes? So we can determine the value of the Q to measure electric charge. What is the maximum value of the electric charge that we can measure using this device? The maximum charge corresponds to the maximum electric force, or actually the maximum X. The maximum X, the maximum displacement of this sphere is D minus 2 times A when this distance is 0. Okay? So when this distance is 0, the maximum X will be equal to D minus 2A. So if we replace the maximum X here, this is the maximum possible electric charge that we can measure using this device. So when we increase the value of the charge, we have more force. So what happens? Nothing. These spheres touch each other and the measurement is wrong after that when the value of the charge is higher, right? And we don't have movement to be able to measure it using this equation. Okay, so yes, not too complex problem, just you should consider the equilibrium condition that we have considering these two forces. Anyway, let's go for the next problem. Problem 2.9. 100 nanocoulombs point charge is located at A, negative 1, 1 and 3 coordinates of the point A in free space. Part A, find the locus of all points P, X, Y, Z at which Ex, the X component of the electric field intensity, is equal to 500 volts per meter. Part B, find Y1 if P0, Y1 and 3 lies on that locus. Again, we should use this equation to find the electric field intensity generated by this point charge. The R, the test point is XYZ, and the source point is negative 1, 1, and 3, R prime. The value of the charge is 100 nanocoulombs. So R minus R prime is X minus negative 1, that is X plus 1, Y minus 1, and Z minus 3. So what is the amplitude of this vector? The amplitude of R minus R prime is this one. Okay? So when we use this equation, we will have this X component for the electric field intensity at the point R generated by the point charge Q. This is the X component. If you replace the value of the epsilon 0 and the point charge, we will have this equation. So according to the part A, we should set the Ex equal to 500 volts per meter. And finally, this equation is the locus of all points, that the electric field intensity, the X component, is equal to 500 volts per meter. Okay? Part B, in the part B, if we set the value of X equal to 0 and the value of the Z equal to 3 in this equation, we will have this equation, and we have two y values that satisfy this equation. Okay, so these are two possible y values for this case. For this case, that the x is 0 and z is 3. Okay, not too complex. Yes, let's go for the next problem. Here also, let's check the numbers 2.9, this problem. Okay, these two values for the y. And this is the solution of the part A. Problem 2.10. A configuration of point charges consists of a single charge of value negative 2q at the origin and two charges of value positive q at locations z equal to negative d and positive d. We have this structure. The charges as positioned form an electric quadrupole. This is an electric quadrupole. We have 4 point charges, two of them are on each other, negative 2 times q. This structure equivalent to two dipoles of opposite directions that are separated by distance d along the z-axis. So let me copy this figure. Here we have these two electric dipoles. This is one electric dipole and this is another one in opposite directions. Okay, so part A, find the electric field intensity E everywhere in the xy plane, expressing your result as a function of cylindrical radius rho in the cylindrical coordinate system. So here again we can use the superposition principle. Yes, we solved this problem. This is the z axis and this is rho. So this problem is equivalent to this problem. Suppose we have 2 point charges here and here, q, positive q and positive q. This is d, the distance. This is d and this problem. This is this plus this z-axis. We should place a point charge here, negative 2 times q. So what is the E electric field intensity in xy plane in this case? For these 2 point charges, we solved it in this problem. Okay, this is the equation. Yes. So this equation that I wrote it here, E. And what is the value of E for this case? Yes, this is a point charge. The value of the electric field intensity for arbitrary value of the rho is k times negative 2 times q divided by rho to the power 2. So the net electric field intensity is summation of these two values. Okay, these two charges and this charge at the origin. Part B, specialize your part A result for large distances when the rho is much higher than d. So in this case, we can use this equation. Yes, we have this important equation from calculus. We can approximate this expression when the value of delta x is small. Yes, we can approximate this expression using this equation 1 plus k times delta x. So when the value of delta x is very low, okay, and compared with 1, we can approximate this expression using this equation. So here In this case, we have this term in denominator here. Okay, so we can approximate this by this equation. Let's factor rho to the power negative 3 first. We will have this equation. Because rho is much higher than d, this fraction is small in compared with 1, delta x, a very small number. So we can approximate this using this equation, and finally we will have this equation. And then we can replace this here instead of this denominator. And then we can simplify this summation. Okay, finally we will have this important equation. This is the value of the electric field intensity on xy plane when the value of the rho is much higher than d. Negative 3 times k times q times d to the power 2 divided by rho to the power 4. Here, the rate of the reduction is faster than electric dipole. Okay, so let's compare for 1 point charge, 1 point charge q. If you consider this radius, the electric field is proportional to 1 divided by r2, r to the power 2. For electric dipole, positive q, negative q, the electric field on xy plane at this radius is proportional to 1 divided by r to the power 3. For quadrupole, positive q and negative 2 times q at the origin and positive q here, the electric field intensity, the magnitude, right here, when the rho is much higher than distance between these point charges, is proportional to 1 divided by r to the power 4. So here we have faster reduction in the value of the electric field intensity. Important, the point of this problem. Okay, so you can use this approximation to prove this equation. Anyway, problem 2.11. A charge q0 located at the origin in free space produces a field for which Ez is equal to 1 kilovolts per meter at this point. Part A, find Q0. How we can calculate Q0? Again, we should use this equation, the electric field intensity generated by a point charge located at this point r prime. So r prime is 0, 0, 0. The location of the source point is the origin. Okay, r is an arbitrary point that we are going to calculate the electric field intensity at it. R minus r prime is x ax plus y ay plus z az. What is the amplitude of r minus r prime? Is this one. Okay, so the electric field intensity generated by the point charge q0 at the point r is equal to this one. And we can calculate the z component. The z component is this one. I calculated 1 divided by 4 pi epsilon 0, that is equal to 9 times 10 to the power 9. I replaced it in this equation. Okay, so let's check what is the value of k. That is 1 divided by 4 times pi times epsilon 0. is close to 9 times 10 to the power 9. So at this point, we know Ez for p equal to negative to 1 and negative 1 x, y, z coordinates of the p. Ez is 1 kilovolts per meter, 1000 volts per meter. We should use SI unit, volts per meter, is equal to this one. And you can calculate Q sub 0. That is equal to negative 1.63 microcoulombs. Okay, this is the solution of the part A. Find electric field intensity at the point M, 1, 6, and 5, its coordinates, in rectangular coordinates, cylindrical coordinates, spherical coordinates. So for the rectangular one, we can replace x, y, z coordinates of the point M in this equation. And here we have the electric field intensity generated by Q0 at the point M, this equation. Okay, that is equal to this one. So we should express this vector in cylindrical coordinates and spherical coordinates, not too complex. As you know, the the electric field intensity generated by a point charge in the spherical coordinate system is radially outward by a positive charge, and by a negative charge is radially inward. Okay, so here we have a negative charge. Yes, so the electric field intensity generated by this point charge is radially inward. And this vector in cylindrical coordinate system, you know that the z component is the same as the rectangular one, and the value of the rho component is equal to this one. We used the equations multiple times in the first chapter. Okay, so the value of the rho is equal to x to the power 2 plus y to the power 2. The vector that we have, the vector is attached to the origin, so simply I can write a square root of 30.1 to the power 2 plus 180.6 to the power 2. That is equal to 183.1. A sub rho minus this. And in the spherical coordinate system, this number is the norm of this vector. Okay? Also, you should consider the negative sign. We solved similar problems multiple times in the chapter 1, so you can refer to the video of the chapter 1, not too complex. So let's go for the next problem, problem 12. Electrons are in random motion in a fixed region in a space. During any 1 microsecond interval, the probability of finding an electron in a subregion of volume 10 to the power negative 15 meter cube. I think we have a typo error here. This is not meter square, is meter cube, is 0.27. This is the probability of finding an electron in this volume. What volume charge density appropriate for such time duration should be assigned to that subregion? As you know, the volume charge density is defined based on average values. Okay, so here the average value is on time, and we have probability of finding electrons in this subregion. What is the charge of electron? The charge of an electron is equal to negative 1.602 times 10 to the power negative 19 coulombs. So the average charge in the volume is the probability of finding electron times the charge of one electron. That is equal to this one. And the volume charge density is the average charge divided by the volume. Okay, this fraction. That is equal to negative 4.32 times 10 to the power negative 5 coulombs per meter cube. Okay, so we calculated the average charge in the volume first, and then we divided it by the volume itself to calculate the charge density, the volume charge density, rho v. So let's go for the next problem. Problem 13. A uniform volume charge density of zero point 0.2 microcoulombs per meter cube is present throughout the spherical shell, extending from r equal to 3 centimeters to r equal to 5 centimeters. If rho v, the volume charge density, is zero elsewhere, find A, the total charge present throughout the shell. How we can calculate the total charge inside this spherical shell? As you know, we should calculate this triple integral. Yes, we have these three cases. For this volume V, for this volume, the total charge inside this volume is triple integral of volume charge density times differential volume dV, this one. Also, we can calculate the total charge on a surface considering surface charge density rho s times differential area. Here, the unit is coulombs per meter cube. Here is coulombs per meter square, and this is coulombs per meter in the case of line charge density. So here the total charge on this line is the line charge density times dl. We should calculate this integral. Okay, so this is our case. The first one, we should calculate this volume integral. This is the differential volume in a spherical coordinate system. You know that we had in the chapter 1 this expression rho v. So what is the bounds for these integration variables? Theta is changing from 0 to pi, phi is changing from 0 to 2 times pi, and r, the lower bound is 3 centimeters, the upper bound is 5. We should use correct units. The correct unit is meter. So we should convert these to meters. So if we replace the value of the volume charge density in this equation, zero point 0.2 times 10 to the power minus 6, this is microcoulombs, okay, times what is the integral of R2 is R3, r to the power 3 divided by 3. The upper bound is 5, lower bound is 3, times 10 to the power negative 6, because this is centimeter. Centimeter to meter is 10 to the power negative 2. Also here we have this power. So this is 10 to the power negative 6 times 2 pi, the integral with respect to phi, and the finally integral of sine of theta, okay, d theta, that is equal to 2 from 0 to pi. Consider that here in this case we have an integral like this. If we have, for example, this triple integral f x gy and hz dx dy dz. In this case, we can write this is integral of fx dx times integral of gy dy. We can separate these integrals. Integral of hz dz. But if, for example, f is a function of x and y, we cannot separate this integral into this form. In this case, we have this separation. So I calculated integrals separately. You know that from calculus. Okay, just a review. So, yes, the total charge inside this spherical shell is 82.1 picocoulombs. Okay, so let's check for this problem. Problem 13 of the chapter 2, 82.1. What is the next part? Find R1 if half the total charge is located in the region R between 3 centimeters and R1. What is the value of the R1? Okay, if we consider this subregion and set the total charge inside this subregion equal to total charge divided by 2, half, we can calculate the value of the R1. Again, we have total charge divided by 2 is equal to this integral. We can calculate this integral, that is equal to this one. R1, okay, can be calculated using this equation, that is equal to 4.24 centimeters. Okay, so not too complex. A straightforward example. So let's go for the next problem. Problem 14. The electron beam in a certain cathode ray tube possesses cylindrical symmetry, and the charge density is represented by this equation. In this case, the volume charge density is a function of rho, distance from the z-axis. This is the case. The unit is picocoulombs per meter cube for rho between 0 and 3 times 10 to the power minus 4 meter, and the volume charge density is 0 for rho higher than 3 times 10 to the power negative 4 meter. Part A, find the total charge per meter along the length of the beam. How we can calculate the Q in 1 meter? So this is the differential volume in the cylindrical coordinate system. This is the volume charge density function, rho v. This equation here, this is because the unit is picocoulombs, 10 to the power negative 12. And let's calculate this integral because we are going to calculate the total charge per meter along the beam. The beam is along the z-axis. So the bound, the lower bound of the z, we can consider 0, and the upper bound equal to 1. Consider that the volume charge density is not a function of z, is only a function of rho. Okay? And what is the bound for phi is from 0 to 2 pi, and from rho is from 0 to 3 times 10 to the power minus 4 meter. Okay? So here, if we calculate this integral, you can calculate this integral. You know that this integral is equal to this one. We have this integral, this equation. You remember, right, from calculus, how to calculate this integral. Integral of rho divided by rho to the power 2 plus a. This pattern we know from calculus. What is the integral of x divided by x to the power 2 plus a dx? If we change this variable, for example, u equal to x to the power 2 plus a, du is 2 times x dx. So instead of x dx, we can write 1 divided by 2 integral of du divided by u. This is ln, right? 1 divided by 2 ln of absolute value of u or absolute value of x to the power 2 plus a. This integral. So I calculated this integral with respect to rho using this equation, and I calculated the integral with respect to phi and z. The total charge in 1 meter is negative 0.72 picocoulombs. So the charge per meter is equal to this one. The Q per meter, if we divide this number by 1 meter, okay, is negative 0.72 picocoulombs per meter. So this is the solution of the part A. Part B, if the electron velocity is 5 times 10 to the power 7 meter per second, and with 1 ampere defined as 1 coulombs per second, find the beam current. So what is the definition of the electric current? The electric current is dq dt. If you consider a cross section, how much charge, how much electric charge is passing through that cross section per unit time. Okay, this is the unit, coulombs per second. 1 ampere is defined as 1 coulombs per second. So here, let's consider this highlighted area. Okay, and we know the velocity. The velocity is in the z direction. This is the value of the v. The beam current is charge per meter times speed. Okay, so the charge per meter, q per meter, or coulombs per meter times speed, meter per second. So this is the unit of the ampere, the current, coulombs per second. That is ampere. Okay, so here we calculated the total charge per meter, and if we multiply it by the speed, we can calculate the value of the beam current. That is negative 36 microampere. Okay, if you consider this highlighted area, right, electrons that have this velocity in the z direction. Okay, so yes, let's go for the next problem. Problem 15. A spherical volume having a 2 micrometer radius contains a uniform volume charge density of 10 to the power 5 coulombs per meter cube. Part A, what total charge is enclosed in the spherical volume? So consider one spherical volume, the radius is given, and the value of the volume charge density is given. We have uniform volume charge density. How much is the total charge that is inside the volume? This is the volume of a sphere. Okay, 4 divided by 3 times pi times r to the power 3. So the total charge is the volume times the volume charge density, because the charge density is uniform. Simply we can multiply the volume by the volume charge density. So if we replace these numbers, the total charge inside the volume is 3.35 picocoulombs. Okay, so let's check the number. Yes, for this problem 15. And what is the part B? Now assume that a large region contains one of these little spheres at every corner of a cubical grid, 3 millimeters on a side, and that there is no charge between the spheres. What is the average volume charge density throughout this large region? So if we have this cubic lattice structure, if we consider only one cell, we will have this cube, okay? And the length of one edge of this cube is given here, 3 millimeters. We can calculate the total charge inside this volume, because this volume repeats, right, in 3D space. Just we considered one cell, so we can calculate the total charge inside this cubic volume and divide by the volume of this cube to calculate the average volume charge density for this region. As you can see here, inside this cube, we have these spherical sections. Okay, so you can count these sections, and as you can see here, only we have one sphere inside this cubic volume. Okay, interesting. So the total charge inside this cube is equal to 3.35 picocoulombs. And if we divide this number by the volume of the cube, the volume of the cube is equal to 3 times 10 to the power negative 3, because this is millimeter. We should change it to meter to the power 3. The volume charge density will be equal to 124 microcoulombs per meter cube. This number. Okay. So this is the solution of this problem. Let's go for the next problem. Problem 2.16. Within a region of free space, charge density is given as rho v equal to rho 0 times r cosine of theta divided by a coulombs per meter cube, where rho sub 0 and a are constants. Find the total charge lying within a, the sphere, r lower than or equal to a, b, the cone, r is lower than or equal a, and theta is between 0 and zero point 0.1 pi. Part C, the region specified by these three constraints. R is lower than or equal to a, theta is between 0 and zero point 0.1 times pi, and phi is between 0 and zero point 0.2 times pi. So like before, we should calculate triple integrals to calculate the total charge in the specified volumes. We have the volume charge density, that is a function of r and theta in the spherical coordinate system. So for the part A, we have this sphere. This is the image of the part a complete sphere. So this is the differential volume. Okay, the upper bound and lower bound of the theta is 0 and pi. Okay, between these two bounds, the phi is between 0 and 2 times pi, and r is between 0 and 8, the radius of the sphere. So just calculation of this integral, we have rho sub 0 divided by a. These two are constants. R times r to the power 2 is r to the power 3. Its integral is r to the power 4 divided by 4. The lower bound is 0, so only we have the upper bound, a to the power 4 divided by 4, and the integral with respect to phi is 2 times pi. Integral with respect to theta, we have sine of theta and cosine of theta here. Okay, cosine of theta here, the integral is 1 divided by 2 sine of theta to the power 2. Yes, if you take derivative of this function, we have sine of theta times cosine of theta from 0 to pi. That is equal to 0. So the net charge inside the sphere is 0 because the charge density is not constant, it's a function of r and theta. The part B, the radius is between 0 and a. The phi is between 0 and 2 pi, but theta in this case is between 0 and zero point 0.1 times pi. We have the same integral. Okay, just we should change the bounds, the lower bound and upper bounds of this term. The lower bound is the same, the upper bound only. Okay, so if you replace 0.1 pi here, we will have this amount of charge in this region, in this cone. Okay, this is the geometry for the part B. The theta is between 0 and zero point 0.1 pi. Okay, and the next case, the part C, also will limit the value of the phi between 0 and zero point 0.2 pi, this case. So again, here calculations are the same. We have these boundaries, upper bound and lower bound for this term. The integral of d phi from 0 to zero point 0.2 pi is 0.2 pi. So this is the amount of the charge in this geometry, in this section. Okay, a portion of the cone, because the phi is between 0 and zero point 0.2 times pi, the geometry of the part C. Anyway, not too complex. Okay, so calculation of triple integrals. Okay, so let's go for the next problem. Problem 17. A length d of line charge lies on the z-axis in free space. The charge density on the line is rho L, positive rho 0 when z is between 0 and d divided by 2, and rho L is negative rho 0. We have negative charge when z is between negative d divided by 2 and 0. Rho 0 is a positive constant. So here we have positive charge and here we have negative line charge. Part A, find the electric field intensity E everywhere in the xy plane, expressing your result as a function of cylindrical radius rho. How we can solve this problem? Okay, until now we calculated the electric field's due point charges. But here in this problem, we have a distributed charge. We have a line charge. So here in reference, in this section, we have an important equation, the field arising from a continuous volume charge or surface or a line charge. Okay, here we have this equation, the field generated by a volume charge. We can extend it for the surface charge or line charge. Okay, this equation. As you know, for a point charge here, for example, for this Q1, when we consider this origin O, this is R1 prime. And if we are going to calculate the field for this location R, we need to calculate R minus R1 prime. Okay, so the electric field generated by this point charge E1 is equal to K Q1 divided by R minus R1 prime to the power 3, the amplitude of this vector to the power 3 times R minus R1 prime. So if we have another charge here, for example Q2, we have this location. This is R2 prime. And again, we can calculate the field. Also, we can use the superposition principle. Here, the value of the E2 is equal to K Q2 divided by R minus R2 prime to the power 3 R minus R2 prime. So if we have a number of point charges here, we can use this summation. The net electric field E at this point P is summation I from 1 to n. For example, we have n point charges, K Q I R minus R I prime times R minus R I prime. This is to the power 3, the amplitude. So we can extend this equation and have it in integral form when we have continuous charge distribution. So in this case, we have this volume integral. This is the differential charge, that is the volume charge density times the differential volume. Okay, so the integral is with respect to prime quantities. You know that. Yes, the integral is with respect to the prime quantities. So yes, we used this equation, actually a simple version of it in the problem 4, when we wrote this for loop. Okay, this for loop is this summation. We considered this point charge and calculated the electric field and added to this variable. So here in this example, we have line charge along the z axis, and we are going to calculate the field on xy plane. So first we should detect the differential charge and then write the integral and then calculate it. This is the z axis. This is the rho, actually in the direction of the xy plane, and we have this charge distribution. I don't know, we can have different functions. Okay, so here when the z is positive, we have positive rho 0, and when z is negative, we have negative but constant distribution. Okay, but we can have arbitrary function. Yes, arbitrary charge distribution, rho L line distribution, that is a function of Z. The unit is coulombs per meter. So, if we consider this differential element, this one, dz, how much charge we have here? The amount of the charge is rho L, the line charge density times dz. In this product, this is dq, differential charge. Consider that dz is positive. This is in the positive. This differential element is in the positive z direction. So the sign of the differential charge is determined by this function. If I plot rho L as a function of z, this is z, this is rho L. This is positive rho 0, this is delta, and this is delta again, negative delta, this is negative rho 0. Here, I consider d equal to 2 times delta. So this is the amount of the charge. Differential line should be positive. And I am going to calculate the field generated by this differential charge, for example, on this point. So this is the test point. We know that the field that is generated by this differential charge is in this direction. So this is the R, the location that we are going to calculate the field. This is R is rho times A sub rho, and R prime is this one. The location of the differential charge is Z times AZ prime. Okay, AZ prime is equal to AZ. So here we have this equation, R minus R prime is rho times A sub rho minus Z prime AZ prime, that is equal to AZ. And the differential electric field generated by this differential charge is equal to K differential charge, yes, rho L dz prime times this quantity, R minus R prime, the absolute value, the amplitude of R minus R prime to the power 3. That is this one. You know that the length of this edge, that is SQ rho to the power 2 plus Z prime to the power 2. So this to the power 3. This denominator that we have here. So the total electric field here is actually the integral of dE from negative delta to delta. The integration is with respect to prime quantities. We have Z. The charge distribution is along the Z axis. So this integral is equal to this one, or actually is equal to integral of negative delta to delta, the first part, the product, right, of this part by A sub rho, and this part that is, right, multiplied by AZ, the AZ quantity. So we have these two integrals, and now let's calculate them. What do you think? This geometry is like an electric dipole, yes, but only we have distributed charge. This is electric dipole, and this is the case that we have this distributed charge. So the field in xy plane must be in the z direction. Yes, we shouldn't have a sub rho component. So let's check. In this integral, we have this function. Yes, inside this integral, the integration is with respect to z prime. And let's check here, if I let me copy this, I want to calculate this integral first. Here we have integral of negative delta to positive delta k rho. The integration is with respect to z prime. Okay, a sub rho, I can write here times this. I can write rho L dz prime, rho L is a function of z prime, divided by rho to the power 2 plus z prime to the power 2 to the power 3 divided by 2. So here we have this constant c. This is equal to c times integral from negative delta to 0. Rho L is negative rho 0. Yes, negative rho 0 dz prime divided by this. Let me, yes. And this part plus c times from 0 to delta. This is rho 0 dz prime again divided by this term. Anyway, let me extend this divided by this term. Okay, so we have these two integrals. Okay, as you know, the function inside this integral, this function, this is a constant. Okay, a positive constant. This is an even function with respect to z prime. Okay, so this integral from 0 to delta is equal to this integral, from negative delta to 0. Also, we have a minus sign here. So the net value is 0. Okay, because this function with respect to z prime is an even function. So we don't have the a row, the row component here, the first term. What about the second term? For the second term, we can write this. This is the second term. So here again, we can write this integral, the second one, into this format. This is k integral from negative delta to 0 z prime dz prime rho to the power 2 plus z prime to the power 2 to the power 3 divided by 2. What is the value of rho L from negative delta to 0 is negative rho 0. Okay, so negative of negative is positive. This is rho sub 0 plus k integral from 0 to delta. We have the same integral here, but the sign of the rho 0, here we have negative rho L. Rho L is positive rho 0. So here we have this sign. Okay, so what do you think? Here, this function with respect to z prime is an odd function. Okay, is an odd function. So this integral is negative. This integral is negative of this integral. And in total, we have this. This summation is equal to negative 2k rho sub 0 integral from 0 to delta z prime dz prime rho to the power 2 plus z prime to the power 2 to the power 3 divided by 2. So How to calculate this integral? How to calculate this integral? Here we have this important integral and we can solve it using change of variable method. This is the format of the integral. In this chapter, we have few important integrals. You should remember them for the exam. This integral is one of them. Okay? Integral of x dx divided by x to the power 2 plus a to the power 2 to the power 1.5. That is 3 divided by 2. So if we consider this variable u, that is equal to x squared plus a squared, du is 2 times x dx, and instead of x dx we can write 1 divided by 2 du u to the power 1.5, or we can write this in this format. And what is the integral here? This is a negative 2 times u to the power negative zero point 0.5, or negative 1 divided by square root of u, or this one. So this is the important integral, one important integral that we have in this chapter. You should remember this for the exam. And the integral of this function from 0 to delta is equal to this one. Okay? 1 divided by square root of a to the power 2, that is 1 divided by a, minus 1 divided by square root of delta to the power 2 plus a to the power 2. So, yes, we can calculate this integral, and finally, we will have this function, this function that is a function of rho in xy plane, the electric field intensity in the xy plane. Yes, so this is the value of this integral. Let me write it here. Is negative 2 times k times rho sub 0 times 1 divided by rho minus 1 divided by square root of rho to the power 2 plus delta to the power 2. This is the electric field intensity. Yes, we can write this also in this format. If we factor rho here, this is equal to negative 2 times k rho 0 rho 1 minus, okay, if we factor rho here, we will have this 1 divided by 1 plus delta divided by rho to the power 2. Or we can write this in this format. This is equal to minus 2 times k rho sub 0 divided by rho 1 minus 1, yes, plus delta divided by rho to the power 2 to the power negative 1 divided by 2. This format that we have here. Okay, so this is the solution of the problem. Let's check the solution from the end of this reference. The problem 17. Here, the D notation is used. I used delta, that is D divided by 2. These two functions are the same. So, now let's go for the part B. Simplify your part A result for the case in which the radius rho is much higher than d, and express this result in terms of charge q, that is rho 0 times d divided by 2. Here we have this distributed charge. Okay, so let me place this here. We need that. Here we have this distributed charge. How much charge we have in the positive z direction here in the positive part, and how much charge here we have. The total charge, the total positive charge is rho 0 times d divided by 2. The total negative charge q minus is negative rho 0 times d divided by 2. So if we consider this condition, this one, to calculate the far field, we have two concepts: near field and far field. Far field. In this case, we are going to calculate the far field when the rho is much higher than d. Again, we can use approximation. Yes, we can use approximation to calculate the far field. Here in this case, if we use this approximation, you know that 1 plus delta x to the power k can be approximated by this equation, delta x, when the variable x is small in compared with 1. So here we can approximate this. This is negative 2k rho sub 0 divided by rho times 1 minus 1 minus 1 divided by 2 times delta to the power 2 rho to the power 2. So 1 minus 1 is 0 minus, right? Negative of 1 divided by 2 is positive. We will have this finally. Negative k rho 0 delta to the power 2 divided by rho to the power 3. Okay? This expression. And we know that rho sub 0 times delta is q. Or actually this is negative k times q times delta divided by rho to the power 3. So this is the far field as a function of rho. As you can see here, the rate of the reduction is proportional to 1 divided by rho to the power 3. This is important. Yes, we can check if we have solved this problem correct or not. We discussed this important point for an electric dipole. Yes, the field on xy plane, the reduction factor is this one, 1 divided by rho to the power 3. And here, for this problem that is similar to an electric dipole, when we see this charge distribution from a long distance. Okay, so we will have the same behavior here. Problem 18a. Find E in the plane z equal to 0 in the xy plane that is produced by a uniform line charge. This rho L extending along the z-axis over the range from the negative L to L in cylindrical coordinate system. So, how we can calculate the electric field generated by this line charge in xy plane? In the previous problem, we had this charge distribution. Negative charge here and positive charge here. But in this problem, we have a uniform line charge. We solved a similar problem, problem 6, using this 2-point charged, we calculated the field, and in this example, as you know, only we had the rho component in xy plane. Okay, here we have a uniform line charge distribution, and again we have the component in the rho direction. So you know that in this case, if we consider this point in xy plane, this is r, okay, that is rho times a sub rho. And if I consider this differential element here, dz prime, that is positive, this differential times rho l is differential charge dq. This is the r prime, that is equal to z prime az prime, that is equal to az, and this is r minus r prime. Its amplitude is square root of rho to the power 2 plus z prime to the power 2. You know that. So in this case, if you consider this differential charge, the electric field produced by it is in this direction, okay, dE. And for any differential charge in the negative side of the z-axis, we have a counterpart differential charge on the positive side that its field is in this direction. The amplitude of these two vectors are equal. So z components cancel each other, and only we have a component in the rho direction. We will prove this also by integrals. So how we can calculate the field in xy plane? Okay, r minus r prime is rho a sub rho minus z prime az. So differential electric field generated by this differential charge is equal to k differential charge, that is rho l dz prime r minus r prime, amplitude of r minus r prime to the power 3, and the net electric field, we should calculate this integral from negative L to L, considering the z prime variable. So here in this integral, if we place this expression, we have this integral that is equal to these two terms, okay, this integral and this integral. So what do you think? Like before, we can interpret these integrals. Here in this integral, we have this function. Rho L is a constant, right? So we have this function, and this is an odd function. Okay, this is an odd function with respect to z prime variable. So the integral from negative L to L is 0. Yes, we don't have z component. And only we have this integral. We should calculate this integral, that is equal to k rho L integral from negative L to L dz prime. Also we can factor rho here, integration is with respect to z prime. This is dz prime divided by rho to the power 2 plus z prime to the power 2 to the power 3 divided by 2, this times a sub rho. So how we can calculate this integral? This is another important integral that we have in this chapter. So we have this pattern, okay, dx divided by x to the power 2 plus a to the power 2 to the power 1.5. In this case, we can use this definition to change the variable, find the variable u. If we consider x equal to a times tangent of u, so dx is a, secant of u to the power 2 du. So x squared plus a squared is equal to a squared secant of u to the power 2. So you can replace this term here, and instead of dx we can use this expression. So if you simplify this expression, we have integral of cosine of u du divided by a to the power 2, a squared. So this integral is sine of u divided by a squared. You know that we considered this definition, and u is tangent inverse of x divided by a. Okay, so this integral dx divided by x squared plus a squared to the power 1.5 is equal to this one. Okay, so this is another important integral that we have. In our case, we know that the function inside this integral is an even function. So this integral is equal to 2 times k rho L rho integral from 0 to L dz prime divided by this. Actually, this expression that we have. So here I can write this for this integral rho to the power 2 plus z prime to the power 2 to the power 3 divided by 2. Here, if I use this pattern, we will have 2k rho L rho times 1 divided by rho to the power 2 sine of tangent inverse of, what do you think? Here we have x, a is rho actually in our equation. This is z prime divided by rho. Okay, so this is the value of this integral. We should calculate this expression from z equal to z prime equal to 0 to z prime equal to L. And as you know, tangent inverse of 0 is 0, sine of 0 is 0, and only we have L component. So we have 2 times k times rho L divided by rho times sine of tangent inverse of L divided by rho. So what do you think here? How we can simplify this expression? If you consider this triangle L rho, this is a square root of rho to the power 2 plus L to the power 2. This is theta, tangent inverse of theta, and then we should take the sine of theta. Okay, the sine of theta is equal to L divided by rho to the power 2 plus L to the power 2 square root. Okay, so finally we will have this expression 2k rho L times L divided by rho times rho to the power 2 plus L to the power 2. Okay, this is the electric field generated by this line charge that is in the rho direction, a sub rho, this expression. Okay, so now let's go for the part B. If the finite line charge is approximated by an infinite line charge L approach to infinity, by what percentage is E sub rho in error? If rho is equal to 0.5 L and C, repeat B with rho equal to 0.1 L. Okay, So we calculated this expression when we have a finite length L. If we extend L from negative infinity to infinity, as you know, in that case, the value of L is much higher than rho. So we can neglect this term. Okay, we can neglect this term. We have a square root of L to the power 2, that is L. We can simplify L's from numerator and denominator, and the value of the electric field intensity when we consider L equal to infinity, a high number, is equal to 2 times K times rho L divided by rho. This is the equation of the electric field intensity for infinite line charge. Okay, this equation. So in this case, this is the approximation. Okay, the E exact divided by the approximation is this one, L divided by a square root of rho to the power 2 plus L to the power 2. And if we calculate this percentage error, approximation minus exact divided by the approximation, if we want to calculate it in percentage, we should multiply this by 100. So we have this equation. In this case, if we set the value of the rho equal to 0.5 L, the error will be equal to 10%, 10.6%. And when rho is equal to zero point 0.1 L, the error is 0.5%. So, what is the point of this problem? Okay, so if we calculate the electric field here close to this line, 0.1 L, zero point 0.1 L is the distance of the point from this line on xy plane. And we have another test point, 0.5 L. Okay, so in this case, when we are close to this line, the electric field is similar to the electric field generated by an infinite line charge. Okay, so yes, when we are going to calculate the electric field intensity close to this finite line, we can use the infinite line charge equation, the electric field, this equation to simplify our calculations. And as you can see here, when we are close to the line, here the distance from the line is 0.1 L. L is the half of the line length. Okay, in this case, the error is very low, 0.5%. And even we consider this number 0.5 L, the error is 10%. And the error increases as long as we consider higher and higher values for rho. Okay, so the point of this important is approximations in our calculations later. Okay, to simplify interpretations. In the previous problems, we extended the value of the rho. We considered high values of the rho to simplify the equation and find the rate of the reduction. In this case, we consider close points near field, and as you can see here, for this near field of this finite line can be approximated by the near field of an infinite line charge. Okay, so this is important. And also we have this important integral in this problem. You should remember this for exam. Anyway, so let's go for the next problem. Problem 19. A line charge having charge density, this line, that is a function of z in this case, rho sub 0, that is a constant number, times the absolute value of Z, coulombs per meter, and our length L is oriented along the Z axis at L divided by 2, 2L divided by 2. The total length of this charge distribution is L. I considered it equal to 2 times delta. Part A, find the electric field intensity E everywhere in the xy plane, expressing your result in cylindrical coordinates. Similar to the previous one, but here in this problem we had a uniform line charge distribution. Here we have a non-uniform. That is a function of Z. As long as we increase it, we have more and more charge. Okay. So here again, as you know, we don't have the Z component. You can realize that the charge distribution is an even function with respect to Z. Only we have the rho component. Okay. Let's check the equation, the calculations. R minus R prime. R is rho A sub rho. This is in the xy plane. R prime is Z prime AZ. dE is K differential charge rho L dZ prime R minus R prime. Amplitude of R minus R prime to the power 3. The net electric field is the integral of dE from negative delta to delta. So replace this into this equation. We have these two terms. We have these two integrals. Okay. And here again, as you can see, this is an odd function with respect to z prime. So the integral from negative delta to delta is 0. And only we have this integral. Yes, let me copy this. Only we have this integral. This is an even function with respect to z prime. So the integral is 2k from 0 to delta rho sub 0 rho z prime dz prime divided by rho squared plus z prime squared to the power 3 divided by 2. What do you think? We had this pattern here, this equation. Yes, we can use this equation to solve this integral. This is equal to 2k rho sub 0 rho. This integral is equal to, if we use this pattern, this integral is 1 divided by rho minus 1 divided by rho to the power 2 plus delta to the power 2, delta squared. I used this pattern. So here is the equation, okay? And we can rewrite this equation in this format. Again, how we can write it? If we factor a rho in this equation, we have 2k rho sub 0 1 minus 1 divided by a square root of 1 plus delta squared rho squared, this equation. And we can write this equation in this format. Part B, evaluate your part A result in the limit as L approaches to infinity, the length. In this equation, if we write increase the value of delta approach to infinity, as you know, this term, this denominator will be very high. So this is 0, and the value of the electric field intensity will be equal to 2 times k times rho sub 0. A sub rho. Okay, this equation. As you can see here in this case, we have a constant electric field intensity that is not a functional rho. Yes, so interesting. We can generate this constant uniform electric field in xy plane by this type of charge distribution. Okay, so let's check the solution of this problem. Yes, the problem 2.19. This is the equation. K is 1 divided by 4 pi epsilon 0. We have the same equation here. So this is important. When you are going to construct a specific field distribution in xy plane, you can modify the charge distribution along the z-axis, different charge distributions that you can generate in practice. Okay, so this is an interesting result derived in this problem. So let's go for the next problem. Problem 20. A line charge of uniform charge density rho sub 0 Coulomb per meter and our length L is oriented along the z axis at from z negative L divided by 2 to L divided by 2 this line charge. Part A, find the electric field strength E in magnitude and direction at any position along the x axis. So we solved this problem. Okay, here is the case. We solved this problem and calculated the electric field intensity in xy plane along this axis, the rho axis. Just we rename this rho axis in this new problem. This is the exact value of the electric field intensity along the a sub rho direction. So here is the equation. Just I renamed rho with x in this case. So electric field intensity, as you know, in this case, for this problem, we don't have electric field intensity in the directional z-axis on xy plane. So here is the value of the E, for example, for this point. Okay, this is direction of the E. Ex is equal to this equation. Part B, with the given line charge in position, find the force acting on an identical line charge that is oriented along the x-axis at x between L divided by 2 to 3 times L divided by 2. So if we have the same line charge here on x-axis, how much force is applied on this line charge due to this line charge? Okay, so here is the differential force. Actually, if we consider this differential charge on this line, the amount of the charge dq is equal to rho sub 0 times dx. Dx is a positive differential element. And how much is the value of the force? We know that F is equal to QE. F applied to this differential charge, dF is equal to rho sub 0 dx times the electric field intensity generated by this line charge. This equation that we have here. Okay, so to calculate the net force, we know that the force is along the x direction, the total force applied on this line of charge is integral of df from L divided by 2 to 3 times L divided by 2. This is the range of integration. And if we replace df here from this equation, we will have this integral. And finally, we should calculate this integral. After the calculation, this is the net force applied on this line of charge that is in x direction. So here, how to solve this integral? This is another important integral that we have in this chapter. This is the process to solve this integral here in this slide. We have this pattern, integral of dx divided by x times x squared plus a squared to the power 1.5. If we use this definition to change the variable x to u, x equal to a divided by u, so dx is negative a du divided by u squared, and we have this expression here. If we replace this and this into this integral, we will have this integral. Okay, and finally we will have this integral. So I can add and subtract 1 to the numerator of this fraction. So we can rewrite this integral in this format into these two integrals. Okay, so what is the integral of du divided by square root of 1 plus u squared? This is the inverse of sine hyperbolic function. Yes, so sine inverse hyperbolic of u minus, what is the value of this integral? We calculated this integral here, this pattern. So this integral is equal to this one. And you know that the inverse of sine hyperbolic function is equal to this one. So yes, using this definition, we can solve this integral. And finally, to calculate this integral from L divided by 2 to 3 times L divided by 2, we should change the bounds, the lower bound and upper bound in terms of u variable, as you know. So in this case, we should change u from 1 to 1 divided by 3. Okay, and then replace these two bounds in this equation and solve. Finally, we will have this equation. You can prove that. Not too complex. Okay. So this is the net force applied on this line of charge. Here in MATLAB, I wrote this M file to visualize this. Here I considered this rho sub 0 an arbitrary number for line charge density. This is epsilon 0, k, and the length for these two line charges equal to 1. I used a numerical integration method. Let me explain. Here in MATLAB, I divided this line of charge into 10 parts. 1, 2, 3, 4, 5, and so on. For each part, we can calculate electric field intensity in the middle of this element using this equation. Okay, and we have this dx variable, so we can calculate the force and finally calculate the net force applied on this line of charge. So here nx is the number of segments. You know, as long as we increase the value of nx, we increase the number of segments, and we can calculate integral numerically, right, better. So here, this is the range of x. We change x from L divided by 2 to 3 times L divided by 2. Dx is here we calculate difference. If we have this vector, for example, 1, 2, 5, 8, 9, diff of x is difference, right? X2 minus x1, 2 minus 1 is 1, 5 minus 2 is 3, 8 minus 5 is 3, and so on. 9 minus 8 is 1. So here I calculated the middle points in the middle of each segment, right? We have actually these segments. This segment, this is x k plus 1. This is xk for this segment. This is the middle point. Dx is equal to xk plus 1 minus xk, and x in the middle, the midpoint, is equal to xk plus xk plus 1 divided by 2. So I interpolate the value of the electric field intensity in this middle point and multiply it by dx to calculate this integral numerically using this for loop. This is the value of fx for each segment, and I implemented this equation here in this for loop to calculate f. Finally, we can plot f, and here I compared the f that I calculated using this for loop and the force that we calculated using this equation that we derived. So let's compare. For this example, if I run this code, as you can see, I calculated two numbers that are the same. If I reduce the number of nx, if I just consider one element, as you can see, this is the value of the force calculated by this equation that is equal to 0.99, and this is the value of the force we calculated using this for loop that is equal to zero point 0.8. Okay, and if I increase the number of segments, for example, to 2, we have a closer result. To 3, we have a closer result. Okay, here I divide this segment into 3 parts and calculate electric field intensity and then force. Here you can see the force vectors. Here we have higher force because this is closer to this line, and we have lower and lower. So if you consider nx equal to 10, as you can see, this is enough to calculate the total force. Apply it on this line charge numerically. These two numbers are the same. Simple for loop. Okay, so as you can see, how we can solve these complex problems numerically, right? Using this simple program, computational electromagnetics. Okay, numerical methods in electromagnetics. Calculation of fields and forces analytically are good because we can interpret the results, we can find relationships. But when the geometries are complex and we cannot solve integrals easily, okay? So it's good if we use a computer, if we use, for example, MATLAB software to solve these problems numerically. This is a good example. So you can practice this code to calculate the force numerically and compare with this equation. Anyway, so let's go for the next problem. Problem 21. A charged filament forms a circle of radius A in the xy plane with its center at the origin. the filament carries uniform line charge density plus rho 0. Here we have positive charge density when phi is between negative pi divided by 2 to pi divided by 2, and negative rho 0 when phi is from pi divided by 2 to 3 times pi divided by 2. So here is the geometry of the problem. Okay, on this circle we have line charge density coulombs per meter. Here we have positive charge density, and here we have negative charge density. Find the electric field intensity E at the origin. So how we can calculate the electric field intensity at the origin? We should find R and R prime for this example, because we are looking for the electric field intensity at the origin. What is the value of the R? The test point is 0 and 0. Yes, the origin. And if I consider this differential element, yes, what is the length of this differential element? Is radius of this circle times d phi. The phi angle is in this direction, positive direction, counterclockwise. Okay, so this is r prime, the location of the source point. R prime is equal to a times a sub rho. A is the radius of the circle. Okay, so r minus r prime is 0 minus a times a sub rho prime. Yes, this prime is important, and we are in cylindrical coordinate system. So dE, the electric field generated by this line charge, you know that it is in this direction, is equal to this one, K times rho L times A d phi prime. This is the differential charge, this product. This is differential length times rho L is differential charge times r minus r prime divided by r minus r prime to the power 3. That is a to the power 3. So to calculate the net electric field intensity at the origin, we should calculate this integral with respect to phi prime quantities from 0 to 2 times pi. And if you replace this in this integral, we will have these two integrals from negative pi divided by 2 to pi divided by 2. The charge density is rho sub 0. Okay, rho L is rho sub 0, and from positive pi divided by 2 to 3 times pi divided by 2, this the line charge density is negative. So we have one negative sign here. This is K rho sub 0 divided by A, this equation. So this equation is equal to negative K rho sub 0 divided by A times these two integrals. So here we have A sub rho prime. Okay, and here A sub rho prime. So here, instead of A sub rho prime, we can write this. You know that the value of the A sub rho in rectangular coordinate system. So we have this integral and this integral. What do you think? Integral of sine of phi prime from negative pi divided by 2 to pi divided by 2 is 0. And we only have the value for this. Then negative of cosine of phi prime d phi prime in this range is 2. For this integral, again, this value is 0, and integral of cosine of phi prime in this range is negative 2. Okay? So 2 minus negative 2 is 4. And here we have this value. In total, the net electric field in this problem at the origin is equal to this one, negative 4k rho sub 0 divided by a in the direction of ax. Yes, we know that. Because of symmetry, the electric field intensity at the origin must be in this direction. Yes, because if you consider this differential element, the field is in this direction. And if you consider this counterpart differential element, the field is in this direction. The y components cancel each other. For this differential element and this differential element, we have the same. So the net electric field intensity must be in this direction. Yes, we can guess this to check if we have solved this problem correct or not. Okay, so this is the solution of this problem. You can practice that. Okay, so let's go for the next problem. Problem 22. Two identical uniform sheet charges with rho s surface charge density 100 nanocoulombs per meter square are located in free space at z equal to plus and minus 2 centimeters. Yes, here you can see the geometry of this problem. Here we have these two sheet charged, and we have this charge density, surface charge density, okay, nanocoulombs per meter square on each of them. What force per unit area does each sheet exert on the other? Okay, so for example, how much is the force per unit area, Newton per meter square, that is applied on this sheet charge? So we need to know the electric field generated by a sheet charge. For example, if we consider this rho s on this plane, we need to know how much is the electric field intensity generated by this sheet charge, and then we can consider this surface element area, okay, this differential area, and calculate this differential force, and finally calculate the integral, okay, to calculate the force per unit area on this sheet charge. So here also you can see this side view of this problem. How much is the electric field intensity generated by a sheet charge? That is equal to rho s surface charge density divided by 2 times epsilon 0. This is derived in this section of the reference chapter 2, field of a sheet of charge. Okay, this one. In the section 2.4, the electric field intensity due to a line charge is derived. Okay, also we derived this equation. Yes, in one of our problems. This is the electric field intensity generated by a line charge. This is in a cylindrical coordinate system, and the field generated by a sheet of charge is calculated considering these lines, right? Here the sheet charge is on YZ plane. Okay, so you can review derivation, not too complex. The value of the electric field intensity is rho s surface charge density divided by 2 times epsilon 0. So here if we consider this sheet charge, the electric field intensity right here is rho s times az divided by 2 times epsilon 0, and in this direction below this sheet is rho s divided by 2 times epsilon 0 times negative az, the direction. The field intensity generated by a sheet charge is perpendicular to it. Okay, so if you consider this side view here, we are talking about these two fields. This electric field intensity generated by this sheet. So, how much is the force? The differential force is equal to differential charge here that we have here in this differential area times electric field intensity that is due to this sheet charge. Okay, so we should consider this one. As you know, the net force that an object can apply on itself is zero. So you shouldn't include the field of the upper sheet when you are calculating the net force on it, right? The force that is applied on this sheet is due to this one. So the electric field intensity is rho s divided by 2 times epsilon 0. This is the unit vector. The differential charge is rho s times differential area. Okay, so here we have this equation. Differential force is rho s times ds. This is differential charge times E. Because the field generated by a sheet of charge is uniform, okay, is also constant. Yes, we don't have z, x, or y. This is a constant number. Also, this is interesting. And yes, you can write df divided by ds is equal to total force divided by area. Okay, we have a uniform force distribution. So the force per unit area is equal to rho s times E, or rho s squared divided by 2 times epsilon 0. And if you replace these numbers here, the total force per unit area is equal to this one. Okay, so let's review this important concept. What is the field generated by a point charge? The definitions. You know that if we have this point charge here, Q, and if you consider this distance R, the electric field intensity in a spherical coordinate system is K times Q divided by R to the power 2 A sub R. What is the field intensity generated by a line charge at the distance rho from this line charge is equal to, this is in this direction, E is in this direction, this is E equal to this equation, line charge. Okay, so you can review derivation, this equation, rho L divided by 2 pi epsilon 0, 2 pi epsilon 0 rho A sub rho. And if we consider this sheet charge with surface charge density rho s, here we have rho L. The electric field intensity here is perpendicular to this surface E, and it is equal to rho s divided by 2 times epsilon 0, a unit vector perpendicular to this normal surface. This equation, in the next section, you can check this equation. So, yes, important equations that we have in this chapter. For a point charge, the electric field intensity E is proportional to 1 divided by R2. For a line charge, E is proportional to 1 divided by rho. And for a surface charge is constant. Okay, so yes, this is interesting. Yes, relationships that we have here. Anyway, so you can review solution of this problem, okay, and derive this number. Anyway, so let's go for the next problem, problem 23. A disk of radius a in the xy plane. Here we have the x-axis, this is the y, and this is z. This is perpendicular to z. This is in the xy plane, carries surface charge density of rho s, that is equal to rho sub s0 divided by rho. When we have increase in the value of the rho, we have reduction in the surface charge density, coulombs per meter square, where rho sub 0, rho s0 is constant. Find the electric field intensity E everywhere on the z-axis. So how we can solve this problem? We should find r prime and r. So we are going to calculate the field on z-axis. For example, this test point. So you know that this is r, the location that we are going to calculate the field at it. And if I consider this differential charge here, this differential charge is equal to surface charge density times differential area. What is the differential area in cylindrical coordinate system? Is rho d phi d rho. Okay, you know that. So yes, this is r prime. R prime. R is equal to Z times AZ. R prime is equal to rho times A sub rho. We have one prime here and prime here. Okay. So this is the distance between R and R prime. What is the value of this distance, this length? This is Z to the power 2 plus rho prime to the power 2. So yes, we can calculate the field. You know that the field generated along the z-axis by this object is along the z-axis, because if you consider this differential charge, the electric field intensity generated by this differential charge is in this direction. And for any differential charge, we have another one on opposite side, that its electric field intensity is in this direction. So radial components cancel each other and only we have z component. How we can prove this? By equations. R minus R prime is Z A sub Z minus rho prime A prime rho. Differential electric field intensity generated by this differential charge dq, this is differential charge, is k times differential charge r minus r prime divided by amplitude of r minus r prime to the power 3. Differential charge is rho s, surface charge density, times differential area, prime quantities, okay, times r minus r prime, and this is r minus r prime, the amplitude, to the power 2, to the power 3, excuse me. So here, if you replace rho s in this equation, instead of differential charge, we have rho s times this. This is rho s0 divided by rho prime. We have one rho prime here. So this is, yes, rho s0 and rho s0 here. We can factor this k rho s0. And finally, we have this integral. Okay. So how to calculate this integral? Let's check here. we have this integral. I used rho 0. This is rho s0. Okay, not important. So you can modify this parameter in these equations. Okay, so yes, let me modify also these two equations anyway. K times rho s0, this double integral. So we have az and a rho prime. First, let's calculate this integral. This integral is equal to, because the integral is with respect to rho prime and d phi prime, we can write factor z from this integral. We have z here. This is a sub z. And this integral is separable. Integral with respect to phi prime is 2 times pi, this integral. So this is 2 pi, and this integral, how we can calculate this integral? Using this equation we discussed before. We have this integral, yes, this important integral in this chapter. So yes, when you calculate these integrals, we will have this equation. This is the AZ component generated by this type of charge distribution, okay, in this problem, this equation. Yes, k times rho s0, 2 pi a divided by z, square root of a to the power 2 plus z to the power 2. What about the second integral? This one, this integral, you know, instead of a rho prime, we can write this equation. Yes, in terms of ax and ay prime, and you know that ax prime is equal to ax and ay prime is equal to ay. So what is the average value of cosine of phi prime and sine of phi prime from 0 to 2 times pi? Is 0. Okay, so this integral, this double integral is 0. We don't have a sub rho component. So yes, this is the electric field intensity along the z axis generated by this. So now let's check, did we calculated this equation correct or not? When the value of, because we have this charge here, if we look at this charge from a long distance, the behavior, right, the rate of reduction should be proportional to 1 divided by r2. Yes. So here in this equation, if we consider z much higher than a, so we have here constant values divided by z to the power 2 is proportional to 1 divided by z squared. So yes, okay. Yes, our calculation is okay. So yes, you can redo calculations and review these integrals. Let's go for the next problem. Problem 24. Part A, find the electric field on the z-axis produced by an annular ring of uniform surface charge density rho s in free space. The ring occupies the region z equal to 0 and rho from A to B. This ring and phi is between 0 and 2 pi in cylindrical coordinates. So here is the geometry of the problem. Okay, this is on the xy plane, and we are going to calculate the field along the z axis. So how we can calculate the field? This is similar to the previous case. Okay, so we have the same differential area. And we have the same equation for distance between differential area r prime and r, but the range of integration for rho is from a to b. Also, we have a constant, a uniform surface charge density. So let's repeat the calculations. Again, r minus r prime is za sub z minus rho prime a sub rho prime. This is differential electric field generated by differential charge. Here we have this differential charge rho s, okay, in free space. I considered rho 0 here. We should change this. This is rho s and is uniform. So these equations, again, we don't have radial component, a rho component, and only we have z component. You can prove that, similar to the previous one. The z component is this one. This is rho s, excuse me, a typo error. I considered rho 0. This is rho s. And here we have this equation. This is the electric field intensity along the z-axis generated by this geometry. So here you can see calculations, integrations. Here also I should use rho s. This is surface charge density. Let me modify these equations, right? These parameters that we have here. Okay, so you can check these equations yourself. Here we have this double integral. The a sub rho component is 0. And here we have this integral. So we have this pattern. You can review. We derived this equation before. Another important integral that we have in this chapter. So after solving this integral, we have this equation. Okay, this important equation that is the solution of this problem. Part B, form your part A result. Obtain the field of an infinite uniform charge sheet charge by taking appropriate limits. So we have this equation. Let me copy this. We derived this equation for this geometry. So if we set the value of A equal to 0, and if we approach B to infinity, actually in this case, we have a uniform sheet charge like this one. Yes, that we have in this section. So this is the electric field intensity generated by a sheet of charge. So let's check here. If we set A equal to 0, this will be equal to 1 divided by Z. Actually, we should consider an absolute value of Z. Okay, so we will discuss. And this, when we approach B to infinity, this will be 0. So we have K, that is 1 divided by 4 pi epsilon 0, times rho s, Z divided by absolute value of Z, okay, times the AZ, that is the unit vector in the Z direction, times 2 pi, okay, this. So yes, this is equal to rho s divided by 2 times epsilon 0, Z divided by absolute value of Z, AZ. So this is actually the sign of Z. Yes, so this says that the field for this side is in positive z direction, and for the negative z direction is in this direction. Okay, so the amplitude is this one, rho s divided by 2 times epsilon 0. That is important, this derivation, this equation. So this is normal vector on sheet charge. Here, the normal vector is along the z-axis, the positive direction, and on the opposite side, the normal vector is in opposite direction of the z-axis. Anyway, so you can write rho s divided by 2 times epsilon 0 times a n, unit vector, the normal unit vector. Anyway, so let's go for the next problem. Problem 25. A disk of radius A in the xy plane carries surface charge of density rho s1 equal to positive rho s0 divided by rho coulombs per meter square when phi is between 0 and pi. Okay, here you can see the geometry of this problem, this red region. And rho s2 equal to negative rho sub s0 divided by rho when phi is between pi and 2 times pi, this blue region, where rho s0 is a constant. Part A, find the electric field intensity E everywhere on the z-axis. Okay, similar to previous problems, let's check and assign R and R prime. We are going to calculate electric field intensity. For example, for this point, this is R vector. R is Z, A sub Z. And if I consider this differential area, again, this is R prime. R prime is rho prime, A sub rho prime. So, as you know, in this case, we shouldn't have Z component. Okay, so you can realize flux lines, electric field intensity streamlines. The field must be in the negative y direction. Okay, so this is similar to an electric dipole. So this is r prime, this is the distance, r minus r prime. We have this equation, r minus r prime is z a sub z minus rho prime a sub rho prime. The electric field generated by this differential charge is k times rho s times differential area. Okay, r minus r prime, r minus r prime to the power 3, the amplitude. So here rho s is equal to this one. We have two integrals, as you can see. When phi is between 0 and pi, the positive charge we have. So this results in this integral, and for phi between pi and 2 times pi, we have this integral. So as you can see here, we can conclude that we don't have a z component, okay, according to these two integrals. So let me write this here. We have these integrals for az component. Let's consider this as a constant. This is c from 0 to pi, 0 to a z, az rho prime to the power 2 plus z squared 3 divided by 2. We have the same integral for this bound. So here, this is plus from pi to 2 pi. the sign is negative. So here we have negative. So this is minus. Okay. So what do you think? We have d rho prime and d phi prime. D phi prime, its integral from 0 to pi is pi. And d phi prime from pi to 2 times pi is also pi, but here we have negative sign. The rests are the same. So the net value is 0. Okay, we don't have AZ component. Only we have a rho component. Again, we should write a rho prime in terms of cosine of phi and sine of phi prime, like this one. Okay, so if you write a phi prime in terms of cosine of phi prime and sine of phi prime, you can prove that the average values for cosine of phi prime is 0 and only we have this term. So you can calculate this double integral using this pattern. Okay, so here we have this pattern for integration, and finally you can derive this equation. So let's save the time. We derived this type of equations multiple times before in the previous problems. So here is the field generated by this electric dipole on z-axis, that is in negative y direction. Part B, specialize your part A result for distances z that is much higher than A. In this equation, if we consider z much higher than A, how we can simplify it? So again, we should use this equation. This is the electric field intensity, negative 4 k rho s0. If I factor z here, we have 1 minus 1 divided by 1 plus a2 divided by z to the power 2, 1 divided by 2 square root. Or we can write this in this term. Again, we have this value, and here we can write 1 minus 1 plus a to the power 2 z to the power 2 negative 1 divided by 2. So we have 1 minus 1 plus 1 divided by 2 a to the power 2 z to the power 2. So finally we can derive this equation. So this is interesting. Yes, the electric field intensity is proportional to 1 divided by z to the power 3 for this condition where z is much higher than a. So let's check here for this problem. We have this rate of the reduction for this dipole. Also for this problem, we have this rate of reduction. So yes, interesting. You can compare solutions of these problems. So let's go for the next problem. Problem 26. Find the electric field intensity on the z-axis produced by a cone surface that carries charge density rho s, that is a function of r in a spherical coordinate system, is equal to rho sub 0 divided by r coulombs per meter square in free space. The cone has its vertex at the origin and occupies the region theta equal to alpha and r between 0 and a and phi between 0 and 2 pi in spherical coordinates. So here is the geometry of the problem. This cone, the vertex is on origin, and we should find the value of the electric field intensity on z-axis. So here you can see these two cross sections of this cone. So the angle alpha is this angle in this problem. The angle alpha is this angle. Okay, so the angle alpha. Differential area for a cone is given in spherical coordinates as dA r times sine of alpha dr d phi. Yes, this is the differential area. Actually, if we consider this differential area on this surface, we need to know this radius, right? Distance of this differential area from the z-axis. So this is alpha, this is r, this is equal to r times sine of alpha times d phi times dr. This is differential area. Part A, find the electric field intensity. How we can calculate the electric field intensity? So yes, let's consider Z positive. I am going to calculate the electric field intensity here along Z axis. The procedure is similar. You can repeat the same when Z is negative. So let's consider this case. So here, if we consider positive side of the Z axis, here, for example, this point, this is R. And if I consider this differential area, this is R prime. This is R minus R prime. So R is Z, A sub Z, and R prime in the spherical coordinate system is R prime A sub R. So here we have R in bold face. Okay, and this is R. So here you can see these two variables, R minus R prime is equal to this one. The differential electric field generated by this differential charge is K times the surface charge density times the differential area, R minus R prime divided by amplitude of R minus R prime to the power 3. What is the amplitude of this vector? Is equal to, this is alpha. We can use the cosine law. We derived the cosine law in the chapter 1. The amplitude of this vector is a square root of z to the power 2 plus r prime to the power 2 minus 2 times z times r prime times cosine of alpha. So to the power 3, this equation. So to calculate the electric field intensity, we should calculate this double integral, change the r prime from 0 to a and phi from 0 to 2 times pi, this integral. So a r prime is equal to this expression. You know that we had this equation in the chapter 1, and you can prove that the average values of cosine of phi prime and sine of phi prime are 0. Yes, the integral is from 0 to 2 pi. We don't have radial component for the electric field intensity, only we have component along the z-axis. You can realize that, similar to previous problems. So here, in this case, we will have this integral, and you can calculate this integral and derive this equation. This is the solution. Okay, the value of the electric field intensity on z axis generated by this cone. Part B, find the total charge on the cone. How we can calculate the total charge? The total charge is double integral of the surface charge density times the differential area. Okay, so here rho s is equal to rho 0 divided by r, and the solution of this integral is equal to 2 pi a rho sub 0 sine of alpha. So part C, specialize your result of part A to the case in which alpha is equal to 90 degrees, at which the cone flattens to a disk in the xy plane. Compare this result to the answer to problem 2.23. So in this equation, if we set the value of alpha equal to 90 degrees, actually we will have this case, this problem. Do we derive this equation or not? Let's check. If we set alpha equal to 90, this is 1, this is 0. So we will have this equation that is the same as this one that we derived here in this problem. So a special case of this geometry is this one. Interesting. So you can compare your solutions between different geometries. The next part D, shows that your part A result become a point charge field when Z is much higher than A. So when the value of the Z is much higher than A, in that case, we can neglect this term, and this term only we have Z to the power 2, square root of it is Z, so this will be Z2, and this is the total charge. Then total charge for this object, the field is equal to K times the total charge divided by Z to the power 2. This is similar to a point charge. Okay, so when we look at this charge distribution from a long distance, the far field is similar to a point charge. Yes. The next part E shows that your part A result becomes an inverse Z dependent E field when Z is much lower than A. So when Z or when A is much higher than Z, in that case we can neglect this part, this part. So we have A, 1A in numerator, we will have this equation. So this is proportional to 1 divided by Z, the near field. Okay, this is proportional to 1 divided by Z. So yes, interesting problem. You can redo the calculations and derive these equations, interpret solutions, compare with solutions of other problems. So let's go for the next problem, problem 27. Given the electric field E equal to this one, find A, the equation of the streamline that passes through the point P 2, 3, and negative 4. B, a unit vector specifying the direction of E at this point. So, first of all, let me explain this. We don't have Z component here in this electric field. Only we have X and Y components. So, this is Z independent. We can neglect these two numbers, okay, and just use X and Y quantities. So how we can find equation of the streamline? What is a streamline? Streamlines are explained in this section. Okay, this concept. A streamline is a good method for displaying the electric field or magnetic fields. Yes, we will use streamlines also in MATLAB to visualize field quantities. In this figure, you can read this subsection. It is mentioned that for a point charge, you can display the surrounding electric field using these methods. The part A, the right subfigure A, you can pick up random points and plot E, but this is not a good visualization. In the part B, you can consider these grid of points uniform and plot these vectors, or you can also show the intensity, right, as using color or thickness here in this graph. To display the relative intensity, we use vectors with different amplitudes. But here we have higher intensity, we use black color, and we have thin vectors when we have lower and lower field intensity. And in this case, we display streamlines and the direction of the field. So this visualization is good. And how we can derive equations of streamlines is actually by solving this first order differential equation. If you consider a vector field and you have complete information about your vector field, you can specify that the field vectors at each point in a space specify the slope of this line, this streamline. So you can write this differential equation. By solving this differential equation, you can find equation of these lines. So here in this problem, dy dx is equal to ey ex, this equation. And here we have ey negative 2 times x plus 4y divided by 4x minus 2y. We can write this equation in this format. This is an exact differential equation. You remember this equation from engineering mathematics course. Yes. So how to solve an exact equation? First, we can take integral with respect to dx. Because this is exact, we can take derivative of u with respect to y, and finally find the solution. So not too complex, okay? Not too complex. You can review these equations. The solution, the u is the solution of this differential equation, the first order, that is a function of x and y. This equation is the equation of streamlines. C is a constant. We can have different streamlines considering different points. This red line shows the streamline that is passing through this point. Okay, so if we consider point P in this equation and replace x and y, the value of C will be 19. So this is the equation of this streamline. Here I have a MATLAB code, how you can generate this interesting figure using MATLAB. Problem 27. Here we have a MATLAB code to generate this vector field and this streamline. So here is the We don't need actually these quantities here in this M file. I generated a mesh grid from -5 to 5 for x and y coordinates. This is ex, ey. So first I generate this quiver plot. Let me run the code, place a breakpoint here and run the code. So here is the vector field. And to plot this streamline, we can use this for loop. I am changing the value of the y from 5 to -1, okay, -0.5 in this case. I consider 100 points, and for each value of the y, I solve this equation to find x. Okay, so in this equation, I change the value of the y and find x using roots function. We used the roots function in the previous video. So here, this is a quadratic equation. We can use roots to find x, and then we store the corresponding value for x. That's all. So if I run this M file, as you can see, we can generate this vector field and this streamline that is passing through this point 3, that is y, and 2 x. Okay, this point. Interesting. So you can repeat calculations. Also, you can write this M file to generate this graph. Part B, a unit vector specifying the direction of E at this point. Not too complex, just you should replace x and y into these equations to calculate ex and ey. So we will have this vector. If we divide it by its norm, its amplitude, we can calculate this unit vector. Anyway, so let's go for the next problem. Problem 28. An electric dipole introduced in problem 2.7 and discussed in detail in section 4.7 consists of 2-point charges of equal and opposite magnitude plus and minus q spaced by distance d, with the charge along the z-axis at positions z plus and minus d divided by 2, with the positive charge at the positive z location. The electric field in spherical coordinates is given by this equation, where R is much higher than D. Okay, we solved this equation. Yes, in the problem number 7, if you consider x, y, and z, consider these 2-point charges, this positive charge here, q, and this negative charge here. So we have this length, this is d divided by 2, and this is d divided by 2. Using rectangular coordinates, determine expressions for the vector force on a point charge of magnitude q at 0, 0, and z. So not too complex. Yes, F is equal to QE is equal to Q times this expression. So this is the electric force applied on this electric charge. So for this point, for a point on z-axis, we have two cases. When z is positive and when z is negative. So as you know, when z is positive, for example, this point, the value of theta in a spherical coordinate system is 0 degrees. So if we replace 0 in this equation, we will have this equation. This is the electric force applied on point charge Q. And for this point, you know that the AR A sub r is in the direction of az, this one. When z is negative, for example, this point, theta is 180 degrees. So if you replace theta in this equation, we will have this equation. Okay? And as you know, if we use z instead of r in this equation and include the negative sign in it, we can write this equation into this term using z and a sub z. So we discussed these equations before, okay, also in the chapter 1. Finally, part B, at a point 0, y and 0. So for this case, the distance, the r distance from origin is the absolute value of y, and theta is equal to 90 degrees, okay, for this point. The value of theta is 90 degrees, and the distance from the origin is absolute value of y. In this case, if you replace theta in this equation, we will have this equation, or actually this equation. We have a theta, and a theta is in the negative direction of the z axis. Here is actually one streamline. Let me plot it. Here, for example, we have this streamline. For this point, the electric field is in this direction, negative az. Okay, only we have az component, its value is equal to this one, proportional to absolute value of y to the power 3. 1 divided by absolute value of y to the power 3. Anyway, not too complex, okay? So let's go for the next problem. Problem 29. If E be equal to 20, E minus 5y. I think we have a typo error here. Okay, this is the correct equation. Times cosine of 5x, ax minus sine of 5x, ay. Find part A, absolute value of E at this point. So here, the absolute value of E, the amplitude of the E vector is equal to 20 e to the power negative 5y, because the amplitude of this vector is 1. Okay, so this is the multiplier. This is the amplitude of E. The amplitude of this vector is cosine of x to the power 2 plus sine of x to the power 2, that is 1. A square root of it is 1. So this is the amplitude of E. For this point, the y is 0.1. If you replace in this equation, the amplitude of E will be equal to 12.13. Part B, a unit vector in the direction of E at the point P. So if we divide this by its norm, its amplitude, we can find E, the electric field intensity, in normalized format. So this is the normalized value, or a unit vector along the electric field intensity at the point P. So here we should replace the value of x is pi divided by 6, that is equal to this one. Yes, straightforward. Part C, the equation of the direction line, the streamline passing through the point P. Here again we have this differential equation. We discussed this differential equation here. Yes, dy dx is equal to ey ex. If we replace these quantities, we have this equation. And this equation, if we take integral from the both sides, we will have this solution. And how we can find the value of this constant number c? We use x, y, z coordinates of this point. So when y is equal to point 1, the x is equal to pi divided by 6. The value of c will be equal to 0.13. Let me check. I think we have a typo error here. Okay. So let's check. 1 divided by 5. Okay. 1 divided by 5 times ln of absolute value of cosine of this expression 5 pi times pi divided by 6. So this number, the negative zero point 0.1, yes, this is close to 0.13, 0.13. Yes, a typo error here. This is zero point 0.1. This is the correct equation. So yes, not too complex problem. Okay, just we should take integral from both sides of this first order differential equation. Okay, so let's go for the next problem. That is the last problem of this chapter, problem 30. For fields that do not vary with z in cylindrical coordinates, the equations of the streamlines are obtained by solving the differential equation E rho divided by E phi equal to d rho divided by rho d phi. Find the equation of the line passing through the point 2, 30 degrees and 0 for the electric field that is equal to this one. So for rectangular coordinate system, we solved this problem. dy dx equal to ey ex to find streamlines for fields that are not a function of z coordinate. In the case of cylindrical coordinate system, when the electric field is not a function of z, we have a similar differential equation. This is E rho, E phi. What is the differential length in the rho direction? Is d rho. The differential length in the phi direction is rho d phi. Okay? So, yes, this differential equation, this is E rho and this is E phi. We will have this equation, and if you take integrals from both sides, we will have this equation. Okay, so you can simplify this equation, and finally we will have this equation. This is a constant c1. This is the equation of this streamline. Okay, this is the vector field in this case, and we have this streamline. How to specify the value of C1? In this problem, we should define the equation of the line passing through this point. So when the value of the rho is 2, the value of the phi is 30 degrees, and we can calculate the value of this constant. So this is the equation of this red line, this streamline. Here in MATLAB, I wrote this code again. Here I change the value of the r and t in the polar coordinate, in cylindrical coordinate. The value of r from 1 to 4 and the value of the phi. Instead of t, it's better if I use phi and rho here. Yes, it's more clear. Cylindrical coordinate system. I calculate x and y coordinates, e rho et. Because I want to use quiver function, I should calculate ex and ey. You know, transformations. Okay, we discussed these transformations. in the chapter 1. First, I construct the mesh grid in cylindrical coordinate system. I calculate x and y points. This is ER, ET in radial and tangential direction in cylindrical coordinate system, EX and EY. Then we plot the vector field, and here we have this equation. I implemented this equation. This is the value of the constant, and this is the value of the rho. This equation that we have here. And the rho is a square root of 2, a square root of 3 divided by sine of 2 times phi. Finally, we can plot this streamline. So if I run this code, as you can see, here we have this vector field and this streamline. Interesting, yes? So I highly suggest to write this code. Change the value of the constant. You can change this point and plot multiple streamlines. So in this figure, I plotted multiple streamlines to visualize the electric field intensity, right, given in this equation. So interesting. Anyway, we have completed all problems of the chapter 2. I hope you found this video useful for your exam. Let's continue solving the problems of the next chapter in the next video.